universe in its infancy was a crucible of unimaginable violence, not the gentle unfolding of time we perceive today, but a cosmic ballet of collision and creation. Our very planet, Earth, was not born of serene accretion, but torn from the fabric of chaos. Imagine a swirling disk of dust and gas, the leftovers from a stellar nursery. Into this nascent chaos, colossal bodies, planetesimals, hurtled with devastating force. These were not minor impacts, but world-shaping cataclysms. Each collision was a searing flash, a shockwave that reordered matter itself. The young Earth was a molten inferno, its surface a churning sea of liquid rock, constantly reshaped by the relentless bombardment from space. And real quick, make sure to subscribe and hit the notification bell for more videos. Now let's keep going. This was not a gentle genesis. This was a raw, elemental forging. The very elements that make up our world today were brought together in this fiery, chaotic dance. Each impact added mass, yes, but it also plastered the surface with new scars, new heat, and new possibilities. But this initial violence was merely the prelude. The true story of Earth's shaping, the story of its deep, hidden layers, begins with the very nature of that early, molten state. And to understand how that molten heart cooled, we must turn to the first great separation, the formation of the core. The young Earth was a sphere of pure, incandescent rage. It pulsed with a heat that made the sun itself seem cool by comparison. Every atom vibrated with the energy of its violent birth. This was the Hadean Aeon, a period so ancient, so alien. It defies our everyday comprehension. We call it hellish, and the name is strangely apt. Imagine a world without oceans, without continents, without even a solid crust to stand upon. Its surface was a vast, churning ocean of magma, a sea of liquid rock that stretched from pole to pole. The air, if you could call it that, was a searing mixture of volcanic gases, a toxic blanket under a sky choked with dust from constant impacts. Yet even in this inferno, a fundamental process was beginning. The densest materials, the heaviest elements, felt the inexorable pull towards the center of this nascent world. It was a slow, inevitable descent. Beneath the roiling surface, a separation was already underway. This was not a peaceful settling. The very act of differentiation released immense heat, adding to the planet's already infernal temperature. It was a self-perpetuating cycle of fire. Each sinking mass of heavy elements ignited new thermal currents within the molten globe. But this primal separation, this descent of the heavy, was not just about heat. It was about creating the very foundations of our planet. It was about forming the heart that would, eons later, drive geological forces. To truly grasp this foundational moment, we must look deeper into the consequence of this fiery sorting, the birth of the core. The descent of heavy elements was a violent cradling. Beneath the surface, a dense sphere began to coalesce, not through gentle accumulation, but through a furious, gravitational embrace. This growing heart of iron and nickel would become the planet's very engine. But the Hadean Aeon was not just about the internal sorting of a solitary world. The solar system itself was a chaotic dance. Planets were still forming, erratically gathering material, their orbits far from stable. And in this tempestuous nursery, a collision of unimaginable scale was about to occur. This was not a mere cosmic fender bender. This was an event that would reshape our world forever. A protoplanet, a world in its own right, about to meet Earth. It was a rogue body, larger than Mars, a celestial wanderer named Theia. The impact was cataclysmic. The sheer force of Theia's collision vaporized much of both bodies. A maelstrom of molten rock and vapor was ejected into orbit. Imagine the sky ripped open, not by lightning, but by pure force. This debris, this incandescent cloud, hung in the void. It was a ring of fire, a swirling testament to the violence of creation. Yet, within this devastation, a new process began to unfold, a slow, gravitational gathering. The ejected material started to clump together. This celestial dust, this consequence of planetary destruction, began to draw itself into a distinct body. It was a moon born from impact, a companion forged in fire. The familiar face of our moon, so often seen as a silent observer, is in fact a scar of cosmic violence, a reminder of the tumultuous birth of our planet and its closest celestial neighbor. And to understand the profound implications of this lunar birth, we must now consider what followed this singular event, the stabilization of Earth and the dawn of a more ordered, yet still volatile, era. The immediate aftermath of the giant impact was not the serene blue sky we know today. Instead, Earth found itself cloaked in a veil of gases, a toxic atmosphere unlike anything we can easily imagine. This primal air was a far cry from the breathable mix of nitrogen and oxygen that sustains life now. This early atmosphere was a volatile brew. It was dominated by gases released from Earth's interior. As it cooled and solidified after the molten chaos of its birth, think of a planet exhaling its inner turmoil. We would find thick clouds of water vapor, yes, but also significant amounts of carbon dioxide, methane, and ammonia. Crucially, there was virtually no free oxygen. It was a suffocating environment, a stark contrast to the breath of life we take for granted. And this dense, unbreathable air offered little protection from the harsh radiation of the young sun. The surface of the young Earth would have been a barren, bombarded place. But even within this seemingly hellish environment, the first hints of what was to come were taking shape. The water vapor, a dominant component, began to condense as the planet slowly cooled. A profound transformation was underway, leading us away from a sky of pure gas and towards something more familiar, though still perilous. Now, to truly grasp the alien nature of this early atmosphere and the slow journey towards habitability, we must delve into the genesis of Earth's oceans. The skies above the still cooling Earth were thick with a suffocating haze. This was not the gentle moisture that forms morning dew, but an immense blanket of steam, a testament to the planet's fiery birth and the violent forces that had shaped it. As the eons began to drift, a slow, almost imperceptible change began to occur. The surface of the Earth, still incredibly hot, started to release some of that intense heat. This gradual cooling allowed the superheated water vapor to do something remarkable. It began to condense. Imagine the entire atmosphere holding its breath, then exhaling as liquid, droplets, then rivers, then vast expanses of water began to form. It was a process so immense, so foundational, that it reshaped the very face of the young planet. The sheer volume of water was staggering. It wasn't just a few puddles or shallow seas. This was a global baptism, a deluge that would come to define Earth's unique character among the rocky planets. But this water was not the clean, pure substance we know today. It was a primeval soup, rich with dissolved minerals and gases leached from the cooling crust. This nascent ocean was acidic, a far cry from the gentle embrace of today's seas. It was charged with the very elements that had been churned up during Earth's formation. The surface was a relentless storm of lightning, and the air itself was heavy with volcanic exhalations. It was a world still raw, still unformed, where the building blocks of life were beginning to stir in this vast, watery crucible. As these first oceans settled, the solid ground beneath them began to interact with this new, pervasive element. The chemical exchanges were profound, setting the stage for untold transformations. But the story of Earth's water is not solely one of condensation. It also speaks of a deeper, more distant origin. To understand the full scope of this watery world, we must consider where else this vital essence might have come from. And that leads us to the bombardment of the early solar system, the Archean Aeon, a name that echoes with the deep rumble of time, marking the dawn of what we now recognize as geological history. This was not a gentle beginning, but a furious, formative era stretching across nearly 2 billion years. Imagine a world painted in shades of red and orange, a landscape forged by volcanic fury and ceaseless bombardment. Continents, small and volatile, were beginning to coalesce from the molten chaos, their edges constantly reshaped by the relentless churn of tectonic plates. Beneath the hazy, oxygen-poor skies, the newly formed oceans, these primordial seas we just touched upon, were the stage for an unprecedented chemical ballet. Dissolved minerals, iron in particular, were abundant, and their presence would soon begin to tell a silent, powerful story etched into the rock record. These early crusts were thinner, more mobile than today's familiar continents. The Earth was a restless place, barely able to hold onto its developing landmasses. Yet within this violent cradle, the fundamental processes that would shape our planet for eons were taking root. The slow dance of creation and destruction was already underway, a rhythm that continues to this day. But to truly grasp the scope of the Archean, we must look beyond the surface to the very materials that built this world, and that requires us to consider the violent origins of our planet and its place in the early solar system, the Archean Aeon, a name that echoes with the deep rumble of time, marking the dawn of what we now recognize as geological history. This was not a gentle beginning, but a furious, formative era stretching across nearly 2 billion years. Imagine a world painted in shades of red and orange, a landscape forged by volcanic fury and ceaseless bombardment. Continents, small and volatile, were beginning to coalesce from the molten chaos, their edges constantly reshaped by the relentless churn of tectonic plates. Beneath the hazy, oxygen-poor skies, the newly formed oceans, these primordial seas we just touched upon, were the stage for an unprecedented chemical ballet. Dissolved minerals, iron in particular, were abundant, and their presence would soon begin to tell a silent, powerful story etched into the rock record. These early crusts were thinner, more mobile than today's familiar continents. The Earth was a restless place, barely able to hold onto its developing landmasses. Yet within this violent cradle, the fundamental processes that would shape our planet for eons were taking root. The slow dance of creation and destruction was already underway, a rhythm that continues to this day. But to truly grasp the scope of the Archean, we must look beyond the surface to the very materials that built this world, and that requires us to consider the violent origins of our planet and its place in the early solar system. The surface of this young Earth was a chaotic canvas, intense heat from radioactive decay deep within the planet, combined with the residual warmth from its formation, kept much of the crust in a semi-molten state. Volcanic activity was not an occasional event, but a constant, pervasive force. Vast lava flows poured across the nascent land, adding new layers to an ever-changing terrain. These early volcanic rocks, though now deeply buried and transformed, are the building blocks of the very first continental crust. But how did these scattered volcanic islands and nascent crustal fragments begin to merge into something resembling continents? It was a process driven by the planet's internal heat engine. Magma, the molten rock beneath the surface, rose and cooled, forming igneous rocks. These rocks, denser and more buoyant than the oceanic crust, began to accumulate. Over time, through a process akin to accretion, these smaller pieces of crust collided and fused, Think of it like countless tiny rafts of hardened lava bumping and sticking together in a restless sea. And what of the materials that would form these first land masses? They were not the familiar granites and sedimentary rocks we see today. Instead, the earliest continental crust was largely basaltic, similar to the rock that makes up the ocean floor, but with subtle differences that allowed it to persist and thicken. This early crust was also rich in minerals like feldspar and quartz, which, when weathered by the harsh conditions of the time, would eventually form the sands of future beaches. As these crustal fragments grew, they began to resist subduction, the process where denser oceanic plates sink back into the mantle. They became, in essence, too light and buoyant to be easily pulled back down. This critical difference, this stubborn persistence, is the key to understanding how the first continents could begin to form and endure. To truly appreciate this monumental shift, we must consider the profound influence of plate tectonics, the grand architect of our planet's surface, deep beneath the churning waves, in the crushing darkness of the primordial ocean floor. Something extraordinary was beginning. Imagine cracks and fissures in the young Earth's crust, places where the planet's internal heat bled outwards. Through these openings, superheated water, rich with dissolved minerals, gushed into the frigid sea. These were the hydrothermal vents, the very cradles where life's first spark may have ignited. The water, heated by the Earth's core, carried an alchemical blend of chemicals: hydrogen sulfide, methane, ammonia, and a host of metals. When this scalding, mineral-laden fluid met the cold ocean water, it caused rapid chemical reactions. Minerals precipitated out, forming strange, chimney-like structures, delicate formations that grew in the hydrothermal plumes. These vents created oases of chemical energy in an otherwise barren, hostile world. Within these mineral-rich environments, complex organic molecules, the building blocks of life, could have spontaneously formed. It was a place of constant chemical exchange, a dynamic soup where simple inorganic compounds were coaxed into more intricate forms. The very surfaces of the vent structures, with their mineral pores and catalytic properties, could have acted as microscopic laboratories, concentrating these rare molecules and facilitating their assembly. But the environment was fleeting, dynamic, and prone to violent eruptions. For life to truly take hold, it needed a more stable environment, a place to build upon these initial, fleeting successes. The secrets of these deep-sea crucibles are still being unlocked, but they hint at a genesis far removed from the sunlit surface, a genesis born of heat, pressure, and the planet's own restless heart. And it is from this deep-sea alchemy that we must turn our gaze upward, towards the sky, to understand the next critical epoch, the emergence of the first true atmosphere. The deep ocean floor, once thought utterly lifeless, reveals its secrets slowly. Here, near the vents, a profound transformation was taking place. It was not a sudden spark of creation, but a gradual dance of chemistry. Molecules, simple at first, began to link together, driven by the energy of the Earth's interior and the unique chemical soup. They formed longer chains, then more complex structures. This was the primordial soup, not in a shallow pond, but in the crushing pressure and darkness of the abyss. These nascent chemical chains, still far from true life, were beginning to exhibit behaviors that hinted at organization. They could self-assemble, draw in new components, and even catalyze further reactions. The mineral surfaces of the vents acted like scaffolding, holding these fragile beginnings in place, shielding them from the harshness of the environment and providing the perfect microreactor for this slow, deliberate construction. But these were not yet cells as we understand them. They lacked a boundary, a self. This is where the true miracle of self-preservation began to stir. A fundamental step was needed, a way to enclose these complex molecules, to create a private internal environment where the dance of chemistry could continue undisturbed. This enclosure, this vital skin, was the precursor to the cell membrane. It allowed the internal chemistry to differentiate from the external world, creating the first true unit of life. These were the prokaryotes, the simplest forms of cellular life ever to exist. They were astonishingly basic. A membrane, some genetic material, and the machinery for self-replication. No nucleus, no complex organelles, just the bare essentials for survival and reproduction. They were single-celled, microscopic entities, yet they represented a monumental leap. They were the first independently living things, capable of harnessing energy, metabolizing, and creating copies of themselves in the deep, dark waters. And in their simplicity, they held a universe of potential. To understand how these tiny pioneers began to shape the planet, we must now consider the very air they would eventually breathe. The first life forms, born in the chemical soup of hydrothermal vents, were hardy survivors. They managed to extract sustenance from the minerals and energy around them, a feat in itself. But their existence was confined to the dark, a world without the sun's radiant power. Yet a profound shift was on the horizon, a revolution that would repaint the very atmosphere of Earth. This pivotal change was the emergence of photosynthesis. Imagine, in the ancient oceans, certain prokaryotes began to develop a remarkable new ability. They learned to harness light from the sun. This wasn't just about getting warmer. It was about tapping into an entirely new, incredibly abundant energy source. They evolved pigment molecules, like tiny solar panels, capable of capturing photons. These pioneering organisms didn't just absorb light. They used its energy to split water molecules. This seemingly simple act had monumental consequences. It released a byproduct, something that was both a waste product for them and a breath of fresh air for the future. This byproduct was oxygen. The first light eaters had arrived, and with them, the slow, steady dawn of an oxygenated world. But how did this oxygen begin to accumulate? And what did it mean for the life that followed? To explore this transformation, we must look to the vast, silent oceans. The oceans, once a realm teeming with life that knew no sunlit surface, began a transformation. Dissolved iron, abundant in the early seas, acted like a sponge. It eagerly accepted the newly released oxygen. This chemical dance, this silent reaction, wasn't a fleeting moment, but a geological epoch. Iron and oxygen combined, forming insoluble iron oxides. These oxides, heavier than water, began to sink. They drifted down, settling on the ocean floor in vast, continuous blankets. Layer upon layer, these iron-rich sediments accumulated over unimaginable stretches of time. These settled materials were compressed, cemented, and transformed into rock. And within these ancient rock strata, we find a breathtaking record. Bands of iron-rich minerals alternate with layers of silica or chert. These are the banded iron formations, or BIFs. Each distinct band speaks of a cycle, a rhythm of oxygen production and iron saturation. They are a stark, visual testament to a world coming into its oxygen-breathing majority. But the presence of these formations also tells us something about the tempo of this change. The bands aren't uniform. Their thickness and distribution reveal periods of intense oxygenation followed by lulls. This ebb and flow of oxygen production, recorded in the very fabric of the planet, hints at a complex interplay between biological innovation and the Earth's chemical environment. It's a narrative written in stone, a story of life's profound impact on our world's atmospheric composition. But these formations also mark the beginnings of a profound chemical shift that would eventually make the surface world habitable for new, more complex forms of life. To truly grasp the scale of this transformation, we must understand the immense geological forces that locked these BIFs away, preserving them for us to find. The banded iron formations, those silent monuments of ancient oceans, whisper of a profound shift. They mark a time when life, in its earliest, simplest forms, began to fundamentally alter the very air we breathe. For billions of years, the Earth's atmosphere held little free oxygen. It was a world of methane, carbon dioxide, and nitrogen, a far cry from the sky above us now. Then came the cyanobacteria. These microscopic organisms, through the remarkable process of photosynthesis, began to release oxygen as a waste product. At first, this oxygen was readily consumed. It reacted with the abundant dissolved iron in the oceans, precipitating out as those striking red and white bands. This was a slow, patient process, a geological conversation measured in millions of years. But eventually, the iron sinks began to fill. The oceans, saturated with oxygen, could no longer absorb it all. The surplus began to escape. It bubbled up across the ancient seas and into the atmosphere. This was not a sudden explosion, but a gradual, inexorable change. A new atmospheric composition began to take hold. The air, once toxic to oxygen-breathing life, was slowly, deliberately being remade. This invisible transformation, painted in the rock record, fundamentally rewrote the rules of planetary evolution. It opened the door for new forms of life to emerge. Life that could harness this potent gas. But this was not a gentle transition. The very oxygen that sustained this burgeoning new life was, by its nature, a reactive force. Its increasing presence began to reshape the chemical landscape of the planet in ways that were both creative and destructive. To understand the true impact of this great oxidation event, we must look at the very air around us and trace its origins back to this pivotal moment, the Proterozoic Eon, a vast expanse of time stretching for nearly 2 billion years, often feels like a hushed interlude in Earth's grand narrative. It followed the turbulent Hadean and Archean, a period of intense volcanic activity and the first stirrings of life. Yet the Proterozoic, meaning earlier life, is a name that hints at more than just a pause. It was a time of immense, slow-moving geological and biological shifts, a deep breath before the more dramatic exhalations of later eras. During these eons, the continents, those massive tectonic plates we recognize today, were slowly coalescing and drifting. Supercontinents, like Rodinia and Pannotia, formed and fractured, their immense gravitational forces shaping ocean basins and mountain ranges over timescales that dwarf human comprehension. These continental movements were not mere background noise. They influenced ocean currents, atmospheric circulation, and crucially, the distribution of nutrients on the planet. The oceans themselves were vast and deep, cradling the early forms of life. Life, though present and diversifying, remained largely microscopic. Bacteria and archaea dominated the biosphere, continuing their silent work of chemical transformation. Photosynthesis, the engine of oxygen production, had begun its slow work, but the atmosphere was still a far cry from the oxygen-rich blanket we know today. You might imagine these shallow, sunlit seas teeming with a hidden world, complex microbial communities carrying out their ancient routines. But beneath this apparent quiet, profound changes were underway. The very foundations of the planet were being laid. The slow dance of tectonic plates, the gradual accumulation of oxygen, and the evolving chemistry of the oceans set the stage for future evolutionary leaps. Yet the dominant characteristic of this era, the one that truly defines its character, is a pervading sense of stillness, a long preamble to the more explosive chapters of Earth's history. It was a time of immense planetary gestation, a period where the fundamental conditions for for more complex life were being patiently, almost imperceptibly, established, leading us to ponder what exactly lay dormant, waiting for its moment to awaken during this long quiet, the silent, microscopic world of the Archean and early Proterozoic eons held its breath. For billions of years, life's story was written in the language of single cells, prokaryotes so simple they lacked even a nucleus. They churned chemistry. They began to oxygenate the planet. But they were a universe apart from what we now recognize as complex life. Then something shifted, a subtle revolution that would ripple through the entirety of biological history. It was not a sudden explosion, but a gradual, almost insidious integration. Within some of these prokaryotic cells, other, even smaller prokaryotes began to find refuge, not as invaders, but as partners. Imagine one cell engulfing another, not to digest it, but to house it. This was the dawn of endosymbiosis, a profound act of biological cooperation that would forge the very building blocks of complexity. These internal guests, once free-living bacteria, began to specialize. Some, capable of harnessing the sun's energy, evolved into what we now call chloroplasts. Others, adept at generating energy through respiration, transformed into mitochondria. These weren't just new organelles, they were entire organisms, now living within a host, their fates inextricably linked. This internal colonization was not a moment of conflict, but a genesis of a new, more capable cellular design. This new cellular architecture, the eukaryotic cell, possessed a nucleus to house its genetic material, a significant upgrade from the free-floating DNA of its predecessors. It had internal compartments, the beginnings of a sophisticated cellular factory. This innovation, slow to spread, but ultimately unstoppable, provided the platform for everything that would follow. It was the essential prerequisite for multicellularity, for the staggering diversity of life that would eventually crawl, swim, and fly across our planet. But how did these nascent eukaryotic cells truly begin to diversify? And what hidden pressures pushed them towards the next great evolutionary threshold? The eukaryotic cell, a marvel of internal symbiosis, had laid the groundwork, but life remained largely a solitary affair. A vast, microscopic world of single-celled architects. Yet, even before the great dramas of complex life unfolded, whispers of something more were stirring. Within certain environments, simple eukaryotic cells began to drift together, not by chance, but by a subtle chemical signaling. They formed loose aggregations, floating colonies where individuals remained distinct, yet shared proximity. Imagine these nascent clusters, a soft gathering of life in the ancient seas. They were like sand grains, loosely held by the tide, each grain a functional unit, but collectively they offered a slight advantage. Perhaps they could better resist currents, or together they could filter more food from the water. This was the earliest hint of multicellularity, not a true organism, but a community of individuals. Some of these colonial forms even developed rudimentary forms of communication, a shared language of molecules that hinted at a unified purpose. But the true leap, the moment when colonies began to shed their individuality and truly merge into a single, cohesive entity, was driven by a potent force. It wasn't just about sticking together. It was about specialization. Certain cells within the drifting mass began to take on specific roles, a division of labor that mirrored the early endosymbiotic partnerships. Some became devoted to movement, others to nutrient capture, and still others to reproduction. This internal diversification was the seed of true multicellularity, transforming a collection of neighbors into a single, integrated life form. How this fragile transition from colony to organism truly solidified, and what environmental shifts may have catalyzed this profound change, leads us to explore the burgeoning world of complex life, where specialization would become the key to survival. The very air we breathe, the breath that sustains us, is a product of a distant, almost unimaginable past. For eons, Earth's atmosphere was a toxic soup, utterly alien to the life we know. But something shifted, a remarkable transformation that would forever alter the planet's trajectory. This was a time when life, in its nascent colonial forms, began to experiment. They were no longer content to simply exist as solitary beings or loose associations. They sought more, and in this seeking, they stumbled upon a powerful chemical reaction: photosynthesis, the ancient art of converting sunlight into energy, was becoming more efficient. As more of this life thrived, more oxygen was released as a byproduct. This wasn't just a little bit of oxygen. We're talking about an atmospheric upheaval, a surge so profound it would be known as the Lama Gundy Jachli event. The oceans began to fill with this new gas, a restless bubbling that altered the very chemistry of the planet. This period saw oxygen levels skyrocket to heights far exceeding anything we experience today. Imagine an atmosphere so rich with oxygen that it might have been toxic to many of the life forms that had previously dominated. This was a great winnowing, a selective pressure of immense magnitude. Life had to adapt or perish. Some ancient organisms, unable to cope with this sudden oxygen abundance, retreated into the anaerobic shadows. Others, however, found a way to harness this new, potent element. This oxygen-rich environment set the stage for a new kind of life to emerge, one that could truly thrive in its presence. To understand how this oxygen boom paved the way for more complex beings, we must now turn our gaze to the consequences of this atmospheric gamble. The oxygen surge, a testament to life's persistent innovation, didn't just change the air, it inadvertently triggered a planetary fever, but not in the way one might expect. Instead of warming, the Earth began to plunge into a deep, chilling embrace. This radical shift in temperature, this first truly global freeze, is known as the Huronian glaciation. It's a concept that strains the imagination. Our vibrant, oxygen-rich planet encased in ice, from the poles to the equator. Picture it: vast ice sheets, miles thick, grinding across continents. Oceans frozen solid, their rhythmic tides silenced. The very breath of the planet, the oxygen that life had so painstakingly produced, seemed to have played a role in its own potential demise. But how could more oxygen lead to such extreme cold? The answer lies in the delicate balance of Earth's atmosphere. Oxygen, while vital for many life forms, reacts readily with methane, a potent greenhouse gas that had kept the early Earth warm. As oxygen levels rose, they steadily consumed this atmospheric blanket, allowing heat to radiate away into space. A slow, inexorable cooling began. This wasn't just a seasonal chill. The Huronian glaciation was an epoch, a period where ice persisted for millions of years. Life, which had just begun to find its footing in an oxygenated world, now faced an existential threat of a different kind. Survival meant finding refuge, finding ways to endure a world encased in frost. But even in the deepest freeze, life finds a way, and the story of this immense glaciation is one of adaptation and the deep, slow rhythms of geological change. To understand how planets recover from such profound cold, we must look to the forces that eventually thawed this frozen world, a process intrinsically linked to the very geological engines that shape our planet. The profound chill of the Huronian glaciation eventually receded, but not without leaving scars on the Earth's nascent crust. As the ice retreated, it sculpted landscapes, leaving behind vast moraines and polished bedrock. Yet the planet was still a work in progress, a dynamic entity still coalescing from chaotic beginnings. Continents, those colossal rafts of rock, were not fixed entities. They drifted, collided, and rifted apart in a slow, ceaseless dance dictated by the restless mantle beneath. Imagine a time when the continents were not scattered across the globe as we know them today. Instead, they were clustered together, a supercontinent in the making. This colossal landmass, known as Rodinia, was a testament to the immense forces of plate tectonics. It wasn't just a single piece of land. It was a mosaic of ancient crustal fragments welded together over eons. This immense concentration of continental mass had profound implications for Earth's climate and its geological processes. The sheer size of Rodinia created vast interior deserts, far removed from the moderating influence of oceans. This altered atmospheric circulation patterns, influencing rainfall and temperature across the globe. But the story of Rodinia is not one of static permanence. Like all supercontinents, it too was destined to break apart. The internal stresses within this colossal landmass began to build, pulling and stretching the crust. This eventual fragmentation would reshape the planet once more, opening new oceans and setting the stage for future geological dramas. To understand the fate of Rodinia, we must explore the forces that would tear this supercontinent asunder, a process that gave birth to new oceans and began the cycle of continental drift anew. The forces that began to tear Rodinia apart were immense. And as these stresses built, a dramatic geological event unfolded. This was the Grenville orogeny, a period of mountain building so vast it truly reshaped the face of the planet. Imagine colossal slabs of Earth's crust grinding against each other, compressing, folding, and uplifting in a geological ballet of unimaginable power. This wasn't a localized tremor or a single mountain range formed. The Grenville orogeny was a globally synchronous event, a widespread tectonic episode that affected continents across the entire planet. It was the ultimate expression of plate tectonics at work, a monumental act of creation and destruction, etched into the very foundations of our world. As these tectonic plates converged, the land buckled and rose, forming mountain chains that dwarfed anything seen in more recent geological times. These were not mere hills. These were titanic ranges, their peaks scraping against the ancient sky. The sheer volume of rock uplifted and deformed during this orogeny left an indelible mark on the geological record. The processes involved were complex, a symphony of subduction, accretion, and collision. Island arcs, oceanic plateaus, and even other continental fragments were scraped off the ocean floor and plastered onto the growing landmasses. It was a period of intense, igneous activity, with vast quantities of magma rising to add to the thickening crust. But the Grenville orogeny was more than just mountain building. It was a fundamental reorganization of Earth's crust. The colossal forces at play not only created mountains, but also thickened the continental lithosphere, creating the stable cratonic cores that would form the heart of future continents. It was a foundational event, a necessary precursor for the subsequent breakup of Rodinia. To understand how these newly formed mountains eventually eroded, and what geological forces then shaped the fragmentation of Rodinia, we must look to the forces of erosion and the subtle shifts in Earth's mantle. The slow breath of the Earth continued, and after the titanic sculpting of the Grenville orogeny, a profound stillness began to settle. Yet within this quietude, a new and chilling chapter was about to unfold. The colossal mountain ranges, born from violent collisions, stood not as eternal sentinels, but as temporary monuments against a rising, icy tide. The very forces that built them, the immense pressures and heat, were reaching a delicate balance, a tipping point that would usher in an era of unparalleled cold. This was the Cryogenian period, a time when the planet itself seemed to fall into a deep, frozen slumber. The familiar rhythms of a dynamic Earth were interrupted by an overwhelming, pervasive chill. It was a time of extremes, a stark contrast to the fiery birth of mountains. The oceans, once vast and temperate, began to lock into an icy embrace. The evidence whispers from ancient rocks, layers of glacial till and dropstones scattered across continents that were once near the equator. These are not the gentle frosts of a single winter, but the enduring scars of an epoch defined by ice. The world was not just dusted with snow, it was encased. But there is a deeper mystery buried within these frozen strata. The glaciers that advanced and receded, carving fjords and smoothing bedrock, did not behave as simple, linear cycles of cold. They tell a story of a world pushed to its absolute limit, a planet teetering on the brink of a permanent freeze. To understand the true depth of this global refrigeration and its peculiar, recurring nature, we must delve into the faintest echoes of a second, even more profound, snowball Earth epic. The ice, thick and ancient, began to surrender. Not gradually, not with a gentle thaw, but with a cataclysmic release. Imagine it. Glaciers kilometers deep, covering the entire planet, suddenly groaning under their own impossible weight. The pressure built the oceans, still mostly frozen, held immense, dissolved carbon dioxide from volcanic outgassing that had been trapped for millennia. As the planet began to warm, though how it began to warm is a question that still echoes in the deep time silence. These trapped gases were unleashed. The thaw wasn't a slow melt, it was a deluge. Gigantic rivers, wider than any on Earth today, surged across continents, carrying unimaginable volumes of meltwater. This wasn't just water finding its way to the sea. This was the planet exhaling, a breath so immense it reshaped coastlines and redefined landscapes. The sheer force of this thawing was such that it stripped away rock, carrying sediments vast distances, leaving behind a geological record of its passage, a testament to an ancient, planet-altering flood. And within this deluge, a new kind of life, or perhaps an ancient life reborn, found its opportunity. The carbon dioxide, now released into the atmosphere in staggering amounts, created a greenhouse effect so potent it drove the planet to the other extreme. But the true legacy of this thaw, the subtle changes it initiated in the very chemistry of our oceans, whispers of a future yet to be defined, a future intimately tied to the return of a more familiar, yet still alien, atmosphere. To understand this transition, we must explore the profound atmospheric shift that followed the snowball Earth thaw. The thaw was not merely a return to normalcy. It was a catalyst. As the planet emerged from its icy slumber, a new chapter began, one written not in rock alone, but in the nascent stirrings of life itself. The seas, once choked with ice and carbon dioxide, began to circulate, carrying nutrients and dissolved minerals across vast distances. It was in this transformed oceanic realm, bathed in the warmer light of a more active sun, that something extraordinary began to emerge. These were not the simple, single-celled organisms that had dominated Earth for billions of years. These were different. They were larger, their forms more intricate, their existence a profound departure from the microbial mats that had been the sole architects of life's early history. These were the Ediacaran biota, the first truly complex multicellular organisms to appear on Earth. Their shapes were unlike anything we recognize today. Some resembled fronds of ferns, others quilted patterns, and many were disc-like or tube-shaped. They lay upon the seafloor, or perhaps floated gently in the currents, engendering a sense of quietude and an alien beauty. But the true mystery of the Ediacaran biota lies not just in their unique forms, but in their very nature. Were they animals? Were they something else entirely? A biological experiment that ultimately failed to find a lasting place in Earth's grand evolutionary narrative. Their fossilized impressions, etched delicately into ancient sandstone, offer tantalizing clues, but leave much to the imagination. The evidence suggests they were sessile, anchored to the seabed, filtering sustenance from the nutrient-rich waters. Yet their sheer size and complexity hinted at a level of biological organization previously unseen. They represented a significant leap in evolutionary innovation, a testament to life's persistence and its boundless capacity for reinvention after periods of extreme planetary stress. The Ediacaran biota occupied a unique niche, existing for tens of millions of years before the dawn of the Cambrian explosion. They thrived in a world that was still finding its footing, a world recovering from cataclysm. But their reign, though remarkable, was finite. The conditions that allowed them to flourish began to change, and their silent forms would soon be overshadowed by a new wave of life. To understand their eventual disappearance and the rise of the more familiar forms that followed, we must look to the very foundation of their existence, the ever-changing chemistry of the ancient seas and the emergence of new predators. The silent seabed of the Ediacaran world held wonders unlike any we know today. Life had found a way to diversify, to build intricate structures, to exist in forms both simple and profoundly strange. Yet something fundamental was missing from this ancient tableau, a driving force that would later propel life into an explosion of complexity and variation. For eons, life reproduced through simpler means, a method of precise duplication, but one that offered little room for novel combinations. Imagine a world where every new generation is an exact copy of the one before. Evolution in such a world would be a glacial process, relying on random, rare mutations to introduce change. But the Earth was not content to wait for such slow, incremental shifts. A truly revolutionary idea was brewing in the deep time of biological history. This revolutionary idea was the harnessing of differences, the elegant dance of genetic material from two distinct sources. It was a concept that would fundamentally alter the trajectory of life on this planet, injecting a potent force of variation and adaptation into the very fabric of existence. It was the dawn of a new era, a biological imperative that promised not just survival, but a dynamic, ever-evolving future. The emergence of sexual reproduction was not a gentle tide, but a seismic shift in the biological landscape. It was a strategy that allowed life to explore an infinitely larger canvas of possibilities. By mixing and matching genetic blueprints, not just once, but continuously, life gained an unprecedented ability to adapt to changing environments, to outwit evolving threats, and to explore novel forms and functions. This biological revolution laid the groundwork for the incredible diversity we see today. But how did this profound change manifest? What were the earliest signs of this new method of inheritance? And what pressures might have driven such an extraordinary evolutionary leap? To truly grasp its significance, we must delve into the very mechanics of life's earliest reproductive innovations, tracing the path that led from simple duplication to the intricate exchange of genetic material, and explore the profound implications of the rise of sexual reproduction, the very ground beneath our feet, the solid foundation of our existence, is not primordial. It is a tapestry woven from cosmic dust, a story of violent accretion and gradual assembly. The Earth, as we know it, did not spring into being fully formed. It condensed from a swirling nebula, a vast disk of gas and dust orbiting our nascent sun billions of years ago. Imagine this primordial disk, a celestial nursery. Tiny particles, mere specks of matter, began to clump together through electrostatic forces. These nascent aggregates grew, their gravitational pull increasing with their mass, attracting more and more material. It was a process of relentless accumulation, a cosmic snowball effect. Each collision, each merger, added to the growing planetary embryo. These impacts were not gentle. They were colossal, energetic events, infusing the young Earth with heat and molten rock. The surface was an inferno, a sea of liquid metal and silicates, constantly reshaped by the bombardment of planetesimals. This chaotic birth, this relentless accretion, laid the fundamental groundwork for everything that followed. But within this fiery crucible, a critical separation began to occur. The heavier elements, like iron and nickel, started to sink towards the center, driven by gravity. This inward pull forged the planet's core, and as this core began to solidify, a profound magnetic field was born, a silent shield that would become essential for life. But the surface remained a volatile work in progress, a testament to its violent beginnings. To understand how this molten chaos began to cool and form the world we inhabit, we must now consider the differentiation of Earth, the very center of our world, a place of unimaginable pressure and heat, began to take its definitive shape, drawn by gravity's unyielding hand. The densest materials, primarily iron and nickel, descended. They plunged through the molten sea, a relentless sinking towards the nascent heart of the planet. This separation was not a gentle settling. It was a violent sorting, a forging of internal strata. As these heavy elements pooled, they formed the planet's core, a dense, metallic heart. It's a realm we can only infer, a place of profound energies that continue to shape our existence. Above this core, the slightly less dense silicate materials began to coalesce. This layer, still fluid and incandescent, would become the mantle. Imagine it as a vast, slowly churning ocean of rock, a reservoir of heat and immense geological force. This internal differentiation, this fundamental division into core and mantle, was the first true architecture of our planet. It created the basic architecture that would dictate everything from plate tectonics to our very atmosphere. But the surface, though cooling, was still a far cry from the stable ground we know. The story of how this cooling continued, and the first whispers of a solid crust emerged, leads us to the formation of the crust. The molten iron and nickel churning deep within the Earth's core were not merely creating heat, they were also generating something far more profound, a palpable, invisible force. As these electrically conductive fluids flowed, they began to spin a vast, dynamic engine. This engine, driven by the planet's rotation and the heat escaping from the core, produced a magnetic field. It was a field that stretched out into space, a protective bubble forming around our nascent world. This was the birth of the magnetosphere. It's a field that acts as our planet's shield. Without it, the relentless stream of charged particles emanating from the young sun, the solar wind, would have stripped away our atmosphere long ago. Imagine a constant barrage, a cosmic exhalation that would scour the surface clean. The magnetosphere deflects most of these particles, guiding them around Earth. This invisible barrier is not static. It writhes and shifts, a living testament to the restless energy within, and its existence is tied directly to the molten dynamo below. But understanding the precise moment this shield became truly effective, and how it interacted with the early solar environment, is a story that draws us further from the core and into the tenuous reaches of space. To grasp its full significance, we must examine the magnetosphere forms shielding Earth from solar wind, the churning heart of the planet, a crucible of unimaginable pressure and heat, was not content to remain hidden. Its internal turmoil found an outward expression, a violent punctuation mark in the slow, unfolding narrative of Earth's youth. Volcanoes, born from the planet's fiery belly, began to erupt. These were not the familiar cones of modern landscapes. These were primal forces, spewing forth molten rock, ash, and gases that would dramatically reshape the young world. The surface, still cooling and consolidating from its birth, was continuously resculpted by this relentless volcanic outpouring. Picture vast plains coated in thick layers of ash, mountain ranges pushed up, and then immediately eroded by the sheer force of eruptions. The very air would have been thick with sulfurous fumes, a constant reminder of the inferno beneath. This was the earth in a perpetual state of creation and destruction. But these eruptions were not just a destructive force. They were also a vital delivery system. The gases released from the planet's interior, carbon dioxide, water vapor, nitrogen, would begin to accumulate, forming the very first atmosphere. It was a slow, deliberate seeding of the sky. The sheer scale of this volcanic activity is difficult to comprehend. Entire continents could have been affected by a single cataclysmic event. The evidence lies buried deep within the rock, in ancient lava flows and ash deposits, a silent testament to this fiery genesis. Yet, this constant, effusive energy also played a crucial role in the planet's thermal regulation, a feedback loop between the molten interior and the hardening crust. To truly understand how this surface was built, layer by fiery layer, we must peer into the forces that drove this relentless upheaval. Volcanic activity shaping the surface of the young Earth. The early moon, a mere newborn, was a far more dynamic and intimate presence in Earth's sky. It hung close, a colossal presence that loomed large and cast an entirely different light upon our nascent world. Its proximity was not a gentle embrace, but a forceful one, dictating rhythms and energies that we can now only faintly perceive. Imagine the tides, not as a gentle ebb and flow, but as titanic surges, vast walls of water crashing against shorelines with an unimaginable ferocity. These were the moon's tidal tugs amplified, a constant, visceral reminder of its gravitational dominion. The Earth's rotation, too, was being dramatically slowed by this intense interaction. But the moon offered more than just gravitational influence. Its surface was a crucible of cosmic bombardment. In its youth, the solar system was a far more chaotic place, a cosmic shooting gallery where asteroids and comets traversed their orbits with reckless abandon. The early moon bore the scars of this violent age, its face pockmarked and cratered by countless impacts. And this ongoing celestial storm was not confined to our satellite. Earth, too, was a target. The moon, in its proximity, acted as a shield, absorbing impacts that might otherwise have devastated our own fragile surface. It was a silent, unacknowledged guardian, taking the brunt of destructive cosmic forces. The sheer energy of these impacts would have been immense, releasing heat and debris that contributed to the planet's evolving environment. It's a story etched not just in lunar dust, but in the very fabric of our own world, a shared history of a volatile cosmic neighborhood. To truly grasp the forces that shaped our planet's early environment, we must understand the volatile dance with the early moon, a closer, more violent neighbor. The very air we breathe, so essential, yet so often overlooked, began its long, slow genesis during these formative eons. It was not a single event, but a series of profound outgassings from the planet's molten interior. Imagine the Earth as a colossal pressure cooker, its core a furnace, its mantle a simmering stew. Volcanic activity, far more rampant and violent than anything we witness today, acted as Earth's lungs. From these fiery vents, a cocktail of gases was released, a primordial breath into the nascent atmosphere. Water vapor, carbon dioxide, nitrogen, and trace amounts of methane and ammonia were the primary components. This initial atmosphere was vastly different from our own. It was thick, hot, and utterly devoid of free oxygen. Sunlight, unfiltered by an ozone layer, would have beaten down with fierce intensity. The skies themselves likely held a peculiar hue, perhaps a perpetual twilight, tinged with the reds and oranges of volcanic dust. And the strange chemistry of this alien air. Yet, within this volatile mix, the seeds of future life were being sown. The constant volcanic outgassing, coupled with the relentless bombardment from space, created an environment of perpetual change. This unseen environmental shift was laying the groundwork for everything that was yet to come. The story of these gases, however, is only part of the picture. To understand how this gaseous shroud truly transformed, we must turn our attention to the formation of the atmosphere, an unseen environmental shift. The nascent Earth was a crucible of elemental forces, and among the most significant, though often unseen, was the growing influence of its lone, colossal companion, the moon. This celestial dance, begun even as the Earth itself was coalescing, would sculpt our planet in ways we can scarcely imagine today. The moon's gravitational pull was not a gentle tug. It was a puissant force, an unseen hand kneading the very crust of our young world. Its presence began to stir the planetary oceans, which were themselves a vast, primordial soup, still steaming from the planet's fiery birth. These initial tides were immense. Imagine waves rising hundreds of feet, not just twice a day, but with a ferocity that reshaped coastlines with every surge. This ceaseless to and fro, this colossal exhalation and inhalation of water, was more than just a geological phenomenon. It was a catalyst. These were the first rumblings of a cosmic engine, set in motion by the synchronized rhythm of Earth and Moon. And as these vast waters began to move, they carried with them the potential for something extraordinary. The very friction of these titanic tides, grinding against the seafloor and churning the water itself, began to introduce a dynamic energy into the nascent oceans. It was an energy that would imbue these waters with a unique character. To understand the deep, slow churn of these primordial seas, we must look to the ocean-moon system. Tidal forces begin to act. The Archean Aeon, a time before the familiar continents began their slow, inexorable drift, was a period where the Earth's crust was forged in a furnace of unimaginable heat and pressure. This was not the solid bedrock we know today, but a more volatile, dynamic shell. It was a world constantly being remade, where volcanic activity was not an exception, but the norm. Vast plumes of magma rose from the planet's core, erupting onto the surface, adding new layers to the nascent crust. These fiery outpourings were the building blocks, the raw material from which the first stable landmasses would eventually emerge. Beneath the seething surface, a slow, internal churning was already at work. Heat from the Earth's interior radiated upwards, a powerful engine driving geological processes. This vast, subterranean furnace was the architect of the Archean crust, shaping it through immense forces we can only infer. But the nature of this early crust was far different from our modern continents. It was thinner, more active, and prone to constant renewal. To truly grasp the solidity that would eventually form the ancient shields of our planet, we step into the Archean crust, the foundation of continents. Long before the continents took shape, before the oceans even had their familiar blue hue, the very essence of our planet was being distilled. Imagine a world still cooling, a molten sphere gradually solidifying. It is in this inferno that the first minerals began to crystallize, not from slow sedimentation, but from the very heart of creation. These were not the complex silicates we see in familiar rocks today, but simpler, more fundamental compounds. Think of fundamental atomic arrangements, coaxed into existence by immense heat and pressure. Each crystal that formed was a tiny, perfect testament to the physical laws governing this primordial chaos. Their emergence was a quiet revolution, a transition from a sea of liquid rock to something with a defined structure. Each mineral grain, however small, represented a point of order in the nascent planetary substance, a foundation upon which future complexity would be built. But the story of these first minerals is not just about their formation. It's about their enduring legacy, how these ancient structures shaped the very chemistry of the early Earth. To understand the foundations of continents, we must first understand the elemental secrets held within the first minerals, building blocks of the planet. We speak of the planet cooling, of minerals crystallizing from the molten heart. But as these solid foundations emerged, a more profound mystery began to stir. It was not from the fire, but from the cooling waters, the simmering primal soup, that a question arose that still echoes through the ages. How could inert matter, the very rocks and minerals we've just discussed, awaken into something vibrant, something that could replicate, consume, and evolve? The transition from non-living to living is a chasm so deep, so profound, that its crossing remains one of science's most persistent enigmas. Consider the sheer improbability. Simple molecules, compelled by circumstance and necessity, began to assemble themselves, not randomly, but with a nascent purpose, forming chains, then structures, then entities that could react to their environment. This was not geology unfolding, but a new kind of alchemy. You've seen the building blocks of planets, the stark beauty of elemental forces, but have you truly considered the moment when those forces, in a peculiar alignment, sparked into what we recognize as life? It's a transformation that challenges our very definition of existence. To probe this impossible leap, we must turn our gaze to the origin of life, a persistent scientific enigma. The planet had cooled. The vast, churning oceans were present, a cradle for an unknown genesis. Yet the earth was not yet the world we know. It was a canvas awaiting its first brushstrokes, and those strokes came not from grand geological events, but from the smallest, most persistent of architects. These were the microbes, the solitary pioneers of the Archean Aeon. They were not merely inhabitants of this nascent world, but its very sculptors. Imagine them, microscopic entities thriving in the primordial soup, a testament to life's tenacious grip. They were the first to harness energy, not from sunlight as we understand it, but from chemical gradients, the very breath of a volcanically active planet. There's a quiet power in the simplicity of these earliest organisms. They were prokaryotes, lacking the complex internal machinery of later life. Yet within their humble forms lay the blueprints for everything that would follow. They processed the world around them, absorbing nutrients, releasing waste, and most crucially, multiplying. This relentless cycle of consumption and reproduction, seemingly mundane, was in fact a profound act of planetary transformation. These microscopic communities, spreading like a silent film across the ocean floor and shallow seas, began to alter the very chemistry of their environment. They were the unseen hands, shaping the Earth's atmosphere and oceans long before any macroscopic life could even dream of existing. This early biological engine was subtle, but its cumulative impact was immense. They were the original miners, the first chemists, working with the raw materials of a young planet, and their legacy is etched into the very rocks beneath our feet. A story told in the strata of ancient sediments. But what was the primary tool, the essential innovation that allowed these nascent architects to begin their monumental work? To understand this, we must look at the origin of life, a persistent scientific enigma. The answer lies not in a single grand event, but in a persistent collective effort. These early microbes, particularly the cyanobacteria, discovered a remarkable process. They learned to use light, not just chemical energy, but sunlight. This was a turning point, a fundamental shift in how life could sustain itself. These photosynthetic pioneers began to extract energy from the sun's rays, a more abundant and reliable source. The byproduct of this miraculous conversion was something we often overlook, something that would eventually fill our skies: oxygen. At first, this oxygen was a poison, a toxic waste product for the anaerobic life that dominated. But life is adaptable. Some organisms evolved ways to tolerate this new gas, and others even learned to use it for their own energy-generating processes. This created a feedback loop, a budding global metabolism. The more photosynthesis occurred, the more oxygen accumulated, and the more oxygen there was, the more opportunities arose for oxygen-based life. These communities often built structures, intricate layered mounds that we call stromatolites. They are, in essence, living fossils. These layered structures, some reaching meters in height, are formed by layers of microbes trapping sediment. They are the ancient cities of the microbial world, testament to their persistent labor. Within these stromatolites, the cyanobacteria engaged in their quiet revolution, laying down layer upon layer, each a snapshot of a moment in deep time. They are windows into a world vastly different from our own, a world where life's very existence was a geological force. They speak of a time when the planet's breath was a slow, deliberate exhalation of oxygen. And these ancient structures, these stromatolites, are not merely relics. They are a direct link to the earliest chapters of Earth's biological epic. They are the tangible evidence of life's ingenuity at its most fundamental level. To truly grasp the impact of these microbial architects, we must next explore the great oxygenation event. The early Earth, far from the predictable rhythms we know, hummed with a different kind of energy. Its atmosphere, a swirling cauldron of gases, held a secret that shaped everything that came after: its carbon cycle. This wasn't a gentle ebb and flow, but a vast, slow dance of elements, a planetary thermostat dictated by forces we can now only glimpse. Carbon, the fundamental building block of life, was also the architect of Earth's early climate. Volcanic outgassing, a constant roar from the planet's interior, spewed vast quantities of carbon dioxide into the atmosphere. This potent greenhouse gas, in concentrations far exceeding today's, trapped the sun's warmth, preventing our nascent planet from freezing. But there was a counterpoint, a subtle whisper in the ancient air: dissolved carbon in the oceans, a reservoir of immense proportions, began to react with silicate rocks. This process, weathering, was incredibly slow, yet over eons, it drew carbon from the atmosphere and locked it away in minerals on the ocean floor. It was a geological exhalation, a slow, deliberate release of heat. This interplay between volcanic input and silicate weathering created a delicate balance. The immense amounts of CO2 kept the planet warm enough for liquid water, but the slow sequestration of carbon meant the climate was not static. It was a world on the edge of a knife, a tightrope walk between a frozen wasteland and a runaway greenhouse. The microbial communities we've touched upon were already beginning to influence this profound cycle. Their early metabolic processes, though seemingly small, were a nascent step towards a more complex carbon economy. They were learning to engage with the very gases that defined their world. Understanding this precarious equilibrium is key, for if this ancient carbon cycle was not so finely tuned, life, as we know it, might never have had its chance to bloom. And to see how this balance shifted, how the very air began to change in preparation for something revolutionary, we must now consider the peculiar nature of the Archean carbon cycle. The oceans, once a vibrant soup of dissolved minerals and nascent life, began to respond to the slow, persistent work of the sun's radiation and the tireless march of microbes. For eons, these single-celled organisms had been quietly, almost imperceptibly, transforming the planet. Their waste products, their very existence, were seeping into the grand, slow rhythm of Earth's chemistry. The subtle shift was in the air itself, while volcanoes belched their fiery breath, and weathering chipped away at mountains. A new player was entering the game of atmospheric composition. Photosynthesis, that elegant dance of light and life, was beginning to make its mark. It was a slow dawn, not a sudden blaze. More and more, oxygen was being released, not in great, sudden gusts, but as a gentle, persistent exhalation from the growing, thriving mats of cyanobacteria. This oxygen, however, did not immediately saturate the atmosphere. It first had to contend with the vast oceans, rich with reduced iron. This iron acted like a sponge, eagerly soaking up the free oxygen. Imagine a vast, slow rust forming across the planet's watery surface, layer by layer. The evidence of this process is etched in the ancient rock record, in the banded iron formations that tell a story of oxidation on a colossal scale. This was the planet slowly, methodically clearing its throat. The atmosphere remained largely anoxic, or at least very low in oxygen, but the seeds of change were sown. The relentless work of photosynthesis continued, a quiet revolution unfolding in the planet's waters. This ongoing process meant that the stage was being set for a monumental shift, a transformation that would ultimately redefine the very air we breathe. And to witness this transition, to understand how these early whispers of oxygen began to coalesce, into something more significant, we must now delve into the slow, deliberate era of the Proterozoic atmosphere, the Proterozoic Eon. 2 billion years of Earth's history, a span so vast it dwarfs human comprehension. During this immense stretch of time, life on Earth continued its quiet, persistent growth. The single-celled organisms that had defined the Archean were not static. They were evolving, adapting, and slowly, imperceptibly, preparing for a leap that would fundamentally alter the trajectory of all life. This period saw the emergence of a truly revolutionary cellular innovation. It was not a mere tweak, but a profound reorganization of the internal architecture of life. Imagine a bustling, chaotic city suddenly discovering a dedicated, protected space for its most vital operations. This new compartment, enclosed by its own membrane, safeguarded the cell's genetic material, its DNA. This was the birth of the nucleus. A membrane-bound organelle, it became the command center, the brain of the cell. It allowed for a new level of control, enabling more complex genetic processes and laying the groundwork for greater specialization within the cell. This was the dawning of eukaryotic life, a pivotal moment hidden within the deep silence of geological time. The implications of this internal enclosure were profound. A quiet revolution that would eventually reshape the biosphere. And to understand just how this internal leap paved the way for entirely new forms of organization, we turn our gaze to the dawn of multicellularity. The emergence of the nucleus within single cells was a profound biological innovation. It was like discovering a hidden vault within the cell, a sacred space where the blueprints of life, the DNA, could be safely stored and meticulously copied. This compartmentalization allowed for far greater genetic sophistication. Now, the cell could manage its genetic information with an unprecedented level of precision, leading to more controlled gene expression and the potential for more complex life forms. This internal restructuring didn't happen overnight. It unfolded over vast stretches of Precambrian time, a slow, deliberate unfolding of biological potential. But the true grandness of this eukaryotic innovation wasn't just in the single, isolated cell. It was in how these newly empowered cells began to interact. They started to form associations, not just loose gatherings, but structured communities. These early eukaryotic ecosystems were a radical departure from anything that had come before. Imagine a vast, silent ocean, no longer populated by mere drifting specks, but by tiny, organized entities, each a marvel of internal engineering. They began to specialize, some perhaps forming protective layers, others developing methods for gathering resources more efficiently. But the question that still echoes through geological time is how these individual eukaryotic cells transcended their solitary existence to become something larger, something more. And to truly grasp the dawn of this new era, we must explore the very beginnings of multicellular life. The silent waters of the Proterozoic Aeon were not the tranquil seas we might imagine. Beneath the surface, a profound and often violent transformation was underway. The very chemistry of Earth's oceans, the primordial soup from which all life would eventually rise, was undergoing a radical alteration. For billions of years, the oceans had been a world of dissolved iron, a metallic blush coloring the deep. Vast quantities of iron, leached from the continents by a young, active planet, filled these waters. This iron was a vital nutrient, but it also played a critical role in the planet's nascent atmosphere. It effectively scavenged any free oxygen that might have formed, keeping the air thin and unbreathable for many forms of life to come. It was a delicate, ancient balance, one that had persisted for eons. But this equilibrium was about to be shattered, not by a cataclysm, but by a quiet, persistent revolution occurring within the tiniest of biological factories. The cyanobacteria, those humble photosynthetic pioneers we've touched upon, had been slowly, steadily releasing oxygen as a byproduct of their sun-powered metabolism. For ages, this oxygen found immediate solace, reacting with the abundant dissolved iron, forming insoluble iron oxides that sank to the ocean floor. Imagine these oxygen molecules, fragile and eager to react, finding their perfect partner in iron, creating the first rust beds of Earth. These banded iron formations, layered like the annals of time, are the silent witnesses to this chemical alchemy. They tell a story of abundance and eventual saturation, as the dissolved iron in the upper oceans began to diminish, depleted by billions of years of this ceaseless rust production. The oxygen had nowhere left to go. It began to accumulate, a slow, inexorable buildup. This marks a critical tipping point, an unnoticed shift in the planet's very breath. The implications of this rising oxygen were immense, a prelude to an entirely new chapter in Earth's history. The stage was being set for life to evolve in ways previously unimaginable. But before the air could truly thicken, before complex life could truly bloom, this oxygen had to contend with the remnants of the old order. To understand the full impact of this burgeoning oxygen, we must explore the consequences of this chemical sea change and the eventual weathering of the iron. The Earth, a canvas of shifting plates, had long held its landmasses in a tight embrace for an unimaginably vast stretch of time. The continents were not the scattered islands we know today, but were instead locked together in a colossal supercontinent. Rodinia, they called it, a name whispered in the geological record, a testament to a time when terrestrial travel meant crossing an entire world of rock and soil. This colossal landmass, a single unified continent, dictated the planet's climate and its oceans in ways we can scarcely comprehend. But the forces that bind can also tear. Deep within the planet's molten heart, immense pressures were building, a slow terrestrial sigh that would eventually fracture this monolithic world. The supercontinent Rodinia, a familiar anchor in Earth's chaotic past, began to show signs of strain. The very foundations of this ancient landmass, weakened by eons of internal turmoil, started to yield. Imagine the immense rock formations groaning under unimaginable stress, a prelude to a global unmooring. This wasn't a sudden cataclysm, no instantaneous shattering. Instead, it was a slow, agonizing divorce playing out over millions of years. Rift valleys, like scars across the planet's face, began to form. These nascent cracks widened, allowing the nascent oceans to creep inland, to assert their claim over the parting land. The once unified crust was being pulled apart, stretched thin, and eventually submerged. The first whispers of a new oceanic domain were being heard. As Rodinia began its reluctant separation, the world's geography was irrevocably altered. Vast new coastlines emerged, and ancient interiors were exposed to the elements. This continental drift was not merely a rearrangement of land. It was a fundamental reshaping of Earth's surface, a process that would influence everything from atmospheric circulation to the distribution of life. The breakup of Rodinia marks a pivotal moment, an era of continental dispersal that would set the stage for dramatic environmental shifts. To truly grasp the scale of these changes, we must look at the very air that began to fill the widening spaces. A subtle shift began to permeate the atmosphere, a change so gradual that its true impact would only be understood by the deep currents of time. This was not the initial surge of oxygen that had momentarily surprised the planet. This was something different, a more profound and sustained alteration, the Neoproterozoic oxygenation event, a second rise that would redefine the very breath of Earth. The remnants of Rodinia's breakup had opened up new basins, vast stretches of shallow sea, where the conditions were becoming ripe for a unique transformation. Photosynthetic organisms, more sophisticated now, found fertile ground in these expanding waters. They were not merely surviving, they were thriving, releasing their life-sustaining gas into the seas, and then, tentatively, into the sky. But this rise was far from straightforward. Unlike the first tentative steps towards an oxygenated world, this event was marked by fluctuations, by pauses and accelerations. It was as if the planet itself was learning to breathe anew, sometimes taking deep, steady inhalations, other times gasping for air amidst cycles of renewal and depletion. We are only beginning to trace the intricate rhythms of this atmospheric evolution, to understand why this second oxygenation was so peculiar, so unlike anything that came before or after. We must delve into the profound interplay between the reborn oceans and the burgeoning atmosphere and discover what lay hidden within the very chemistry of this slow, terrestrial sigh. The world, it seems, had not yet decided on its final form. The slow breathing of the earth, that tentative rise in atmospheric oxygen, was soon to be met by a force of unimaginable power. A chill began to creep across the planet, not merely a winter's embrace, but a deep, abiding cold that would come to define an age. This was the onset of the Marinon glaciation, a period so profound that it threatened to extinguish the very sparks of life that had begun to flicker. Imagine oceans, once teeming with nascent life, now freezing over. Imagine continents, still adrift and reconfiguring, being entombed in ice. This was not just a scattering of frozen landscapes. This was a global encapsulation. The ice sheets, thick and relentless, crept from the poles, and some evidence even suggests they burrowed their way across the equator itself. The Earth, in essence, was becoming a snowball. The sheer scale of this freeze is difficult to comprehend. It was a time when the planet's very hydrology was fundamentally altered, when the familiar cycles of water were suspended beneath a crystalline shroud. You might wonder, how could life persist under such crushing, frozen conditions? Were there pockets of warmth, hidden refuges where the torch of existence could be passed? Or was this truly the Great Silencing, a doomsday event written in glacial ice? To understand the survival of life through this deepest freeze, we must look for the subtle whispers of warmth that defied the overwhelming cold. The crushing weight of the Marinon glaciation could not last forever. Even the most formidable ice ages eventually yield to the slow, inexorable forces of geological time, as the vast ice sheets that had locked the planet in their grip began to thin and retreat. A profound warming began to take hold. This was not a gentle thaw, but a powerful resurgence of heat, a planetary fever that would fundamentally reshape the world. What caused this dramatic shift from a frozen wasteland to a burgeoning warmth? It's a question that echoes through the rock layers, a mystery etched in the chemical signatures of ancient oceans. As the ice retreated, it carried with it vast stores of carbon, locked away for millennia. This carbon, mostly in the form of CO2, was released back into the atmosphere. A little is good, but imagine vast mountains of ice melting, exposing rock that then weathers, releasing even more. This atmospheric surge of greenhouse gases, like a thick blanket, began to trap the sun's energy with unprecedented efficiency. The temperature rose and rose and rose. The oceans, once choked with ice, began to stir. But this rapid warming came with its own set of challenges. The sheer influx of carbon and nutrients from the melting glaciers had a dramatic, almost explosive effect on the biosphere. You might imagine a silent world suddenly roaring back to life. But the transition was far from simple. The end of Snowball Earth was not just about the ice melting away. It was about what came next. To truly grasp the post-glacial world, we need to understand the explosion of life that followed this immense warming and the strange new forms it began to take, hinting at the deep shifts happening within the Earth's very chemistry. The retreating ice sheets left behind a world transformed, a canvas wiped clean by a global thaw, and upon this freshly painted surface, something remarkable began to stir. Life, which had for so long clung to the fringes, now surged forth with a startling audacity. This was not a gradual unfolding, but a blossoming, a sudden proliferation of forms, unlike anything that had come before. These were the Ediacaran biota, a collection of organisms that defy easy categorization, leaving paleontologists to ponder their very nature. They were soft-bodied, often appearing as fronds, discs, or quilted patterns etched into ancient seafloor sediments. Imagine strange botanical gardens spread across the ocean floor, unfurling in the dim, filtered light. Some drifted, others lay still, their purpose enigmatic, their place in the grand tapestry of evolution a profound puzzle. But the Ediacaran biota were more than just peculiar shapes. Their emergence marked a pivotal moment, the first hints of multicellular complexity on a scale previously unseen. They were the vanguard of a new era, a testament to life's tenacious drive to explore every possibility. Yet within their alien forms lay the seeds of future diversity, a silent promise of the vibrant ecosystems that would soon follow. To understand this nascent explosion of life, we need to delve deeper into the conditions that allowed such radically new forms to take root, and consider the possibility that these early experiments foreshadowed innovations that would reshape life's very blueprint. The answers lie in the quiet sedimentation of the ocean floor, where these enigmatic organisms first made their appearance. The Ediacaran whispers faded, replaced by a growing rumble, a shift in the very rhythm of existence. The ancient seabed, once a canvas for ethereal fronds and quilted forms, began to stir with a new kind of energy. This was not merely the appearance of new shapes, but a fundamental reordering of the biosphere, a momentous transition into an age of clear visibility and undeniable definition. Life was no longer content to exist in the shadows of possibility. It was ready to be seen, to be known, to leave its indelible mark. This seismic shift, this epochal change, is known as the dawn of the Phanerozoic. The word itself, Phanerozoic, carries the weight of revelation, meaning visible life. It is a name that speaks to a profound unveiling, an era where the scattered experiments of the Ediacaran period coalesced into a dazzling, complex, and interconnected web. The world was about to become a much more crowded and dynamic place, teeming with creatures that would shape continents and oceans for eons to come. The transition was marked by an explosion of diversity, a sudden blossoming of forms that would leave future generations of scientists in awe. It was as if the earth itself had exhaled, and a myriad of new beings sprang forth, each a testament to life's boundless creativity. This was an age where shells began to appear, where skeletons began to form, and where the intricate dance of predator and prey would begin to sculpt the evolutionary landscape. But what primal forces were at play, transforming the quiet, alien gardens of the Ediacaran into the vibrant, bustling ecosystems of the Phanerozoic? The story of this transformation is etched in the layers of rock, a narrative of change waiting to be deciphered. The quietude of the Ediacaran gave way to thunderous creation. Imagine the seafloor, once painted with the soft, enigmatic forms of early life, now erupting with a feverish energy. This was not a slow, gradual unfolding, but a sudden, almost violent blossoming of animal blueprints. Nearly every major animal phylum we recognize today, the fundamental body plans that define the very essence of animal existence, appeared within a remarkably short span of geological time. This rapid diversification, often called the Cambrian explosion, is one of the most profound puzzles in Earth's history. It's as if a switch was flipped, and the evolutionary potential that had been gestating for billions of years was finally unleashed. New appendages sprouted, eyes evolved, and the intricate machinery of complex bodies began to whir. But within this burst of novelty, certain forms began to dominate, laying the groundwork for the ecosystems that would follow. This wasn't just about more species. It was about fundamentally different ways of being alive. Hard parts, like shells and exoskeletons, emerged, offering protection and new avenues for movement and feeding. The ocean depths, once a realm of gentle drifting, became a stage for intricate interactions, the first whispers of predator and prey. To understand how this breathtaking array of life came to be, we must turn our gaze to the foundational shifts that enabled such a profound biological revolution, a revolution we will explore as we delve into the rise of the trilobites. Imagine a world finally ready for complex forms. The oceans, once a canvas for simpler, softer beings, began to teem with creatures possessing a new kind of armor. Among these emerging architects of the Paleozoic seas, one group rose to spectacular prominence. They were the trilobites, a lineage of arthropods that would come to dominate the marine world for hundreds of millions of years. Their very name, three-lobed, hints at their distinctive, segmented bodies, encased in exoskeletons. These ancient arthropods were masters of design, finely tuned to the environments they inhabited. They scuttled across the seafloor, burrowed into the sediment, and even swam through the water column. But the exoskeleton, while offering protection, also presented a fundamental challenge. This protective shell was shed and regrown, a process that left them vulnerable during the molting period. The diversity within the trilobite world was staggering. over 30,000 species have been identified, each adapted to a particular niche. Some were tiny, no bigger than a grain of rice, while others grew to impressive lengths. Their segmented bodies, often divided into a cephalon head, a thorax, and a pygidium tail, provided a blueprint that proved remarkably successful. And within these ancient forms, we begin to see the echoes of challenges that would shape life for epochs to come, a story that pulls us toward the shadow of their greatest competition, the very emergence of specialized predators that would test their resilience. The trilobites, with their intricate segmented bodies and hard exoskeletons, were indeed formidable inhabitants of the Cambrian seas. Yet their evolutionary success was not a simple, unopposed ascent. The very complexity that allowed them to thrive also created new avenues of vulnerability, and indeed new pressures upon other forms of life. Beneath the waves, where sunlight filtered dimly through the ancient waters, a silent drama was unfolding. It was a time of rapid diversification, a biological explosion that left a fossil record both wondrous and frustratingly incomplete. The world was beginning to demand more of its inhabitants, pushing them toward greater specialization. And then, as if painted by a cosmic brush, a unique window into this ancient world was opened. In the Canadian Rockies, a mountain range that now stands sentinel over millennia, lies a deposit of rock that holds within it an unparalleled collection of preserved life. This is the Burgess Shale, a treasure trove that continues to whisper secrets of the Cambrian. Here, amidst the ordinary, lie creatures of astonishing strangeness and beauty. The shale, formed from fine mud that settled in a deep, oxygen-poor basin, acted as a perfect tomb. It captured the ephemeral, the soft tissues, the delicate appendages that are so rarely preserved. It's as if time itself paused, holding its breath to show us a forgotten menagerie. These fossils reveal an ecosystem teeming with forms unlike anything we might imagine. They showcase the raw experimentation of life before the age of familiar skeletons, and shells truly took hold. We see swimming predators with grasping limbs, armored worms with rows of spines, and bizarre filter feeders. What lies within the Burgess Shale is not merely a collection of ancient creatures, but a testament to the sheer, unbridled creativity of evolution. It tells us that the blueprints for life, even in its earliest, most experimental phases, were far more diverse than we might have initially supposed. Yet, as we examine these alien forms, a crucial question surfaces. How did such complex and varied life emerge so rapidly, and what geological conditions allowed for this unprecedented preservation? For what we will explore next in the peculiar alchemy of soft tissue preservation, the Cambrian explosion, with its burst of novel forms, left us awestruck, but it was merely a prelude. Following this initial surge, a period of profound expansion began, a time when life in the oceans truly found its footing and diversified at an astonishing rate. This is the era of the Great Ordovician Biodiversification Event, a time when the seas became a canvas for an explosion of new species and ecological complexity. Imagine the oceans of the early Ordovician, vast, teeming, and rapidly filling with new niches. The foundations laid in the Cambrian allowed life to explore, to refine, and to multiply. New predators emerged, developing sophisticated hunting strategies, while their prey evolved equally intricate defenses. This intricate dance of predator and prey spurred further innovation, a relentless cycle of adaptation. The shallow seas, bathed in sunlight and rich with nutrients, became the nurseries for this grand diversification. Entirely new groups of organisms established themselves, from the humble brachiopods that carpeted the seafloor to the coiled shells of cephalopods that patrolled the water column. Even the very structure of the seafloor began to change as burrowing organisms reshaped the sediment, creating new habitats. But the sheer scale of this event, the sudden and widespread appearance of so many new forms, forces us to ask what geological and chemical shifts were truly powering this oceanic renaissance, and to understand the conditions that allowed life to flourish so dramatically, we must look to the changing chemistry of the oceans themselves, a transformation that would unlock even greater diversity. The waters of the Ordovician, once a simpler broth, began to develop intricate structures, much like the cities of today rise from the earth. These were not the coral reefs we know, built by calcium carbonate skeletons. Instead, a different kind of architect was at work, primarily massive colonies of filter-feeding organisms like tabulate corals and different types of stromatoporids. Ancient sponge-like creatures formed the bedrock of these nascent reef systems. They were sessile, anchored to the seafloor, patiently building upwards, layer by painstaking layer. These structures created complex three-dimensional environments, offering shelter and food sources where before there was only flat expanse. Within these burgeoning reefs, a vibrant community began to assemble. Small trilobites scuttled across their surfaces, seeking out nooks and crannies. Gastropods and other mollusks grazed on microbial mats that grew in the sheltered waters. Fish, still relatively primitive in form, began to navigate these new underwater landscapes, adding another element of complexity. These early reefs were more than just passive structures. They were active participants in the marine ecosystem, altering local currents, trapping sediment, and creating microhabitats that fostered even greater biodiversity. The very presence of these complex, built environments fundamentally changed the carrying capacity of the oceans, allowing more life to exist and to specialize. But what was it about the Ordovician oceans that allowed these massive, organized builders to thrive and create such extensive structures, and as life became more complex within these sheltered domains, what larger, more global forces were at play, shaping the very stage upon which these intricate ecosystems were unfolding. To understand the foundation of these vibrant reef cities, we must delve into the changing mineralogy of the seafloor and the shifting pressures from the distant stars. The thriving life of the Ordovician seas, so carefully constructed and so richly diverse, was not to last. A shadow began to creep across the oceans, a chilling prelude to a devastating event that would reshape the biosphere. The vibrant, complex world built on the seafloor, teeming with trilobites and primitive fish navigating the sheltered reefs, was about to face an unimaginable crisis. This was no slow decline, no gradual fading. It was a sudden, violent severing of life's threads. The very foundations upon which this flourishing ecosystem had been built began to crumble. The conditions that had fostered such growth were reversing with a speed and ferocity that life simply could not adapt to. The fossil record bears witness to this abrupt end. Entire groups of organisms, so prevalent and successful just moments before in geological time, vanish without a trace. The intricate tapestry of life, woven over millions of years, was torn asunder in a geological blink. But what could precipitate such a widespread and catastrophic loss of life across the globe? What cosmic or terrestrial shift could silence so much of the vibrant symphony of the Ordovician oceans? To comprehend the scale of this devastation, we must explore the chilling events that marked the Endordovician extinction. The oceans, once a graveyard, began to stir again. The suffocating grip of the extinction event loosened its hold, and life, tenacious and unyielding, started to reclaim its dominion. This was the dawn of the Silurian period, a time of tentative recovery and astonishing diversification. The world, scarred but not broken, offered a blank canvas for evolution's artistry. The shallow seas, now emptier but no less inviting, became cradles for new forms. Organisms that had survived the purge found themselves in a world with reduced competition, allowing them to explore new niches and possibilities. It was as if the earth itself exhaled a sigh of relief, and with that breath, life was gifted a second chance. This recovery wasn't a simple return to what was, but a radical reimagining. We see evidence of this resurgence in the fossil layers, where the silence of the extinction begins to break with the emergence of new species. The survivors, no longer confined by the pressures of a crowded Ordovician world, began to branch out, to adapt, and to thrive. The slow, patient work of rebuilding the biosphere commenced, layer by fossilized layer. But the rebuilding was not uniform. Some groups, once dominant, struggled to regain their footing, while others, previously minor players, rose to prominence. This era of recovery also laid the groundwork for a new burst of innovation, a period where life would truly begin to explore the boundaries of its potential. To understand how this resilient life reshaped the planet, we must explore the early Silurian world and the forces that guided its remarkable reawakening. The waters of the early Silurian teemed with a quiet energy, a palpable sense of something new stirring beneath the surface, a promise whispered in the gentle currents. The devastation of the Ordovician had cleared the stage, and life, ever resourceful, was beginning to fill the void. Yet the creatures emerging from this period were not merely echoes of the past. They were a bold declaration of evolution's intent, a testament to its unyielding drive towards complexity, towards agency. Among the most significant of these nascent innovations were the very first vertebrates to wield a true jaw. Before this time, aquatic life gnawed and filtered, employing brute force or passive consumption. But here, in these ancient seas, a new paradigm was dawning. The jaw, a simple yet revolutionary structure, was more than just an appendage. For eating, it was the birth of true predation as we understand it. Imagine a mouth that could open and close with purpose, lined with structures capable of seizing and holding. This was not just a dietary advantage. It was a fundamental shift in the ecological dance. Suddenly, the ocean floor was not just a place to graze or hide. It was a hunting ground. The very fabric of marine existence began to alter, threaded with the new tension of predator and prey. These early jawed fishes, often armored and formidable, were the pioneers of a new kind of life. They were the first to truly act upon their environment in a profoundly predatory way. Their existence reshaped the food webs, forcing other organisms into new defensive strategies, accelerating the arms race of evolution. But how did this crucial innovation arise? And what were the initial forms that embodied this evolutionary leap? To understand this transformation, we must look to the specific adaptations that allowed these early predators to emerge from the Silurian depths. The oceans teemed with life, a vibrant and complex tapestry woven over eons. But a whisper of change was stirring, a call to a new realm. It was a transformation so profound it would repaint the very face of the planet, a shift from the blue to the green. For ages, the land remained a stark, desolate canvas, a place of rock and dust, untouched by the flourishing of life that characterized the seas. Yet the relentless pulse of evolution, always seeking new frontiers, began to exert its influence. From the water's edge, a tentative vanguard emerged. These were not the grand creatures of the deep, but something far humbler, yet infinitely more significant. These were the first land plants. Their arrival was not a sudden explosion, but a slow, painstaking colonization. Imagine the sheer audacity of it. This primitive flora, pushing against the alien environment of the dry earth, facing harsh sunlight and volatile weather. They were pioneers in the truest sense, each cell a testament to resilience. These early terrestrial plants were simple, moss-like, or fern-like in form. They clung to the damp margins of lakes and rivers, their roots seeking purchase in the soil, their leaves unfurling to capture the sun's energy. They were, in essence, creating their own world, inch by painstaking inch. This quiet invasion was the genesis of an ecosystem that would eventually cover the globe. It was the beginning of a green revolution that would irrevocably alter the atmosphere, the climate, and the very course of biological history. And as these first, hardy plants established their tentative hold, they began the monumental task of transforming the barren continents, setting the stage for a world unseen. To truly grasp the magnitude of this terrestrial rebirth, we must delve into the specific evolutionary pressures that guided these nascent green pioneers onto the land. The quiet spread of plant life onto land marked the dawn of a new era. It was an evolutionary triumph, a slow conquest of a seemingly insurmountable frontier. These early terrestrial plants, though humble in appearance, were architects of a revolution. They began to anchor the soil, to draw nutrients from the rock and earth, and most crucially, they started to exhale a gas that would change everything. As their numbers grew, these pioneers of the land transformed the barren landscape. What was once a desolate expanse began to show the first hints of green. This was no mere aesthetic change. The roots of these plants, like ancient miners, fractured the rocks, releasing vital minerals. Their fallen leaves and decaying matter enriched the soil, creating a fertile substrate where life could truly take hold. This was the Devonian period, a time of incredible diversification and transformation. While the land was being slowly painted green, the oceans, which had long been the cradle of life, were experiencing their own golden age. This was the age of fishes. Within the vast, watery expanses, an astonishing array of fish began to flourish. From the shallow coastal waters to the deepest abysses, these aquatic beings evolved into forms, both familiar and utterly alien. Armored giants patrolled the ancient seas, their bony plates a formidable defense. Delicate, schooling fish darted through vibrant coral reefs, a testament to the burgeoning complexity of marine ecosystems. The Devonian seas teemed with life in a way that had never been seen before. This explosion of piscine diversity was not just about numbers. It was about innovation. New body plans emerged, new feeding strategies were perfected, and new ecological niches were filled. The oceans were a vibrant, active world, a stark contrast to the still nascent terrestrial environments. But the story of the Devonian is not simply one of separate, concurrent evolutions. The changes on land and in the sea were deeply intertwined. The very act of plants taking root on continents began to shape the oceans, altering their chemistry and currents in subtle yet profound ways. And as this aquatic renaissance reached its zenith, a new question began to surface. What evolutionary pressures drove the first complex vertebrates to not only survive, but to thrive in these ancient waters, and what would eventually lead some of them to look beyond the safety of the waves? To understand this, we must examine the deep-sea dwellers that laid the foundation for this piscine explosion, and how their ancient lineage set the stage for a dynasty of aquatic dominance. The weight of an ancient world pressed down, a world teetering on the edge of a profound transformation. For eons, life had been a creature of the water, bound to its embrace, its currents dictating every pulse of existence. But the seeds of a radical departure had been sown. The land, once a barren expanse, was slowly being softened by the persistent greening of plant life. This green frontier, however, remained largely uninhabited by creatures of significant size or complexity. Yet, within the teeming Devonian seas, a change was brewing. It wasn't a sudden eruption, but a slow, deliberate reshaping of evolutionary trajectories. Among the myriad of fish, some began to develop a remarkable set of adaptations. These were not merely passive swimmers, but creatures exploring the very boundaries of their watery realm. They possessed sturdy fins, capable of more than just propulsion. These fins, in some lineages, were evolving into something akin to limbs. Skeletal structures within them grew stronger, more robust, hinting at a potential to bear weight. Internal changes also became evident, particularly within their respiratory systems. The gills, the ancient organs of aquatic life, were being complemented by something new, something that suggested an ability to draw breath from the air itself. This transitional phase was a quiet revolution. It unfolded in the murky shallows, where the water met the land, a liminal space pregnant with possibility. These pioneers were not leaving the sea entirely, but were testing its edges, driven by pressures we can only glimpse through the fossil record. What forces compelled these vertebrates to venture into this alien environment? What unseen advantages lay beyond the familiar embrace of the ocean? To truly grasp this monumental shift, we must delve into the early experiments of these amphibious pioneers and explore the very first steps that marked the vertebrates' conquest of land. The oceans, once a vibrant tapestry of Devonian life, began to fray. A shadow cast by unseen forces fell across the waters. It was a profound stillness that crept in, a silencing of the vibrant chorus that had echoed through the seas for millions of years. This was not a swift, violent end, but a slow, gnawing decline. The bustling reef systems, the complex ecosystems that had taken eons to build, started to crumble. Familiar coral architectures, once teeming with a dizzying array of fish and invertebrates, became desolate. Many species, highly specialized to their particular niches within these vibrant communities, found themselves adrift without anchor. their intricate relationships, their delicate balances, could not withstand the encroaching emptiness. The very fabric of marine biodiversity began to unravel. Entire groups, which had flourished for ages, saw their numbers dwindle with alarming speed. It was as if the immense creative surge of the Devonian had reached a breaking point, and the earth, in a slow, deep exhalation, began to reclaim what it had so generously given. The question that hangs in the silent, ancient waters is not merely what died, but what mechanisms of devastation could orchestrate such a widespread and profound loss. How did the very foundations of marine existence begin to collapse? And what echoes of this catastrophe would linger, shaping the future of life on this planet? To understand this dying, we must look closer at the late Devonian extinction and its devastating blow to marine life. The air itself seemed to thicken, not with the scent of decay you might expect after such a widespread loss, but with a potent, growing vitality. A transformation was underway, a slow metamorphosis of the planet's very breath. The oceans, though scarred, had begun to clear, and the land, once a more subdued canvas, was about to explode with a verdant, relentless energy. Vast, sprawling swamps began to dominate the continents. These were not the shallow marshes of today, but immense, humid forests stretching across the lowlands. Gigantic ferns, some reaching heights of 30 meters, unfurled their fronds. Strange, alien-looking horsetails, as thick as tree trunks, stood sentinel. Mosses and primitive seed plants created an almost impenetrable carpet, blanketing the fertile, waterlogged earth. Here, life found a new, almost overwhelming expression. The world was becoming a single, massive, living organism, exhaling a dense, oxygen-rich atmosphere. This colossal botanical engine was more than just scenery. It was actively reshaping the planet's chemistry, burying itself with an astonishing vigor. And within these ancient, shadowed wetlands, a new kind of abundance was being locked away. A fundamental shift was occurring in how this planet stored its energy, a process that would leave an indelible mark on the chapters of time, yet to unfold. To truly grasp the scale of this organic revolution, we must delve into the heart of the Carboniferous period, the vast coal swamps that formed. The air hung thick and heavy with moisture, a humid shroud clinging to the colossal flora. Sunlight dappled through the immense fronds of tree ferns, casting shifting patterns on the spongy ground below. It was here, amidst this primeval, verdant explosion, that the planet's arthropods found their moment of unparalleled dominion. Imagine a world where the very architecture of life had been fundamentally altered. Insects, already established players, now swelled to proportions that defy modern comprehension. Dragonflies, their wingspans rivaling that of large birds, patrolled the skies, their multifaceted eyes gleaming with an ancient, alien intelligence, scanned the dense canopy. these were not the timid creatures we know. They were apex predators in their own right, masters of the humid air. And they were not alone. Millipedes, some as long as a human arm, navigated the forest floor, their segmented bodies leaving trails through the decaying leaf litter. Spiders, their webs woven with silken strength between giant stalks, waited patiently for their prey. This era, the Carboniferous, was a unique confluence of environmental factors. The high oxygen levels, a direct consequence of the rampant plant growth, and the burial of organic matter played a crucial role. A higher concentration of oxygen in the atmosphere allowed these invertebrates, which rely on diffusion for respiration, to grow to such gargantuan sizes. Their tracheal systems, the network of tubes that deliver oxygen to their tissues, became far more efficient. But what was the ultimate fate of this insectoid empire as the planet's atmosphere began to shift once more? A subtle change in the buried layers of carbon hinted at a coming equilibrium. And to understand the delicate balance that brought these giants down to size, we must examine the geological forces driving the end of the great coal swamps, the immense forests of the Carboniferous, teeming with life and breathing out an oxygen-rich atmosphere, were a vibrant experiment. But the very success of these carbon-sequestering plants set the stage for a dramatic planetary transformation. Beneath the surface, a slow, inexorable force was gathering strength. Continents, like colossal rafts upon the mantle, were not static. They drifted, they nudged, and sometimes they collided. The vast, single ocean that had once cradled these early landmasses began to fragment. Tectonic plates, vast puzzles of Earth's crust, shifted with agonizing slowness. Over millions of years, these movements redirected ocean currents and altered atmospheric patterns. The coal swamps, once thriving in predictable climates, found themselves on paths that would lead to profound change. This was the dawn of a new geological epoch, one defined by connection, not of life, but of land. The separate continents, each with its unique geological history and evolving life forms, were being drawn together. It was a planetary embrace, a colossal tectonic waltz that would reshape the very map of the world. Imagine, if you can, the immense pressure building deep within the Earth. Mountains born of earlier collisions would be reworked, uplifted, and eventually eroded. Shallow seas, once barriers between landmasses, would be squeezed out of existence, their watery beds becoming dry plains. This grand convergence was not a singular event, but a protracted process, a symphony of geological forces playing out across timescales that dwarf human experience. The landmasses began their slow march toward unification, a prelude to the formation of Pangaea. This grand assembly would create supercontinents, altering climates and ecosystems on a scale never before witnessed. But what were the initial consequences of this continental drift? and the first stages of this immense collision, and how did it impact the delicate atmospheric balance maintained by those ancient carbon-rich swamps. To find out, we must look to the nascent stages of Pangaea's formation. The Permian period hangs in the balance, a vast geologic breath between two dramatically different worlds. It is a time bridge, a chasm spanned by Earth's slow, relentless transformation. Here, the echoes of the Carboniferous, with its lush, swampy forests, begin to fade, and the harbingers of a more arid, more unified planet start to make themselves known. Continents, once scattered like islands across the globe, were beginning their inexorable journey towards a singular supercontinent. This was not a sudden event, but a grand, slow-motion ballet of tectonic plates. The vast oceans that separated them were shrinking, giving way to the immense pressures that would eventually weld them together. It was a period of immense geological upheaval, where the very fabric of the planet's surface was being rewoven. Mountains, some familiar, others long eroded into memory, were being born anew from the colossal forces of collision. The ancient rhythms of life, once dictated by diverse, separate environments, now faced a world that was becoming increasingly homogenized. But this immense geographic shift was more than just a rearrangement of land and sea. It was a fundamental alteration of global climate. The abundant moisture that fueled the Carboniferous swamps began to recede, replaced by drier conditions. This change played a critical role in shaping the life that would persist and the life that would eventually vanish. As the continents converged, the vast shallow seas of previous eras began to disappear. Their sediments, once a testament to a marine world teeming with life, were compressed and uplifted. These emerging landmasses, pushed and pulled by the Earth's inner fire, created new mountain ranges and vast continental interiors, far from the moderating influence of the ocean. The air itself began to change, with the diminishing of widespread, waterlogged vegetation. The atmospheric composition started to shift. The balance of gases, so crucial for the life that had thrived, was put under new strain. This period was laying the groundwork for profound changes, a slow tightening of the planetary grip that would test the resilience of all living things. The Permian, then, is not just a chapter in Earth's history. It is a profound transition. It's where the great Carboniferous experiment in abundance met the crucible of continental unification. And as these landmasses locked together, forming the early stages of Pangaea, the world was set on a path towards a dramatic and unprecedented environmental challenge. To understand the consequences of this growing landmass and its impact on atmospheric chemistry, we must look further into the heart of this coalescing world, exploring the rise of the great supercontinent itself, the slow continental grind, the uplift and subsidence of ancient seabeds was not merely a geological ballet. It was also a stage, upon which entirely new forms of life were beginning to emerge. As the world consolidated, a particular lineage of amniotes, those ancient egg-laying reptiles that had ventured onto land, began to diversify in ways that would echo through the deepest reaches of time. Among these burgeoning groups, one stood out with a nascent promise. These were the synapsids, a diverse collection of creatures that, at first glance, might seem like mere variations on the reptilian theme. Yet, within their skeletal structure, a subtle but crucial difference emerged. A single opening in the skull behind each eye socket. This anatomical feature, this synapsid notch, was not an accident of design. It allowed for greater space for jaw muscles, a more powerful bite, but its significance runs deeper than mere predatory efficiency. This alteration in cranial architecture hinted at a more complex physiology, a potential for greater metabolic control. It was a whisper of the future, a subtle divergence that set them apart from their anapsid cousins, who possessed no such openings. These were the very first glimmers of what would eventually lead to us. The Permian world, with its shifting climates and consolidating continents, provided the perfect crucible for these innovations. While many ancient lineages struggled and eventually faded, the synapsids, with their adaptive advantages, began to carve out a more prominent niche. They were a testament to life's persistent drive to explore new possibilities, even as the planet itself seemed to be drawing its breath in preparation for immense change. The emergence of these animal ancestors, these pioneers of the synapsid line, presages a future of profound terrestrial transformation. And to truly grasp the scale of these impending shifts, we must now turn our gaze to the very air that these creatures breathed, and the monumental alteration it was about to undergo. The Permian world, so rich with the burgeoning diversity of synapsids, was not an eternal stage. A silent tremor began beneath the surface, a buildup of pressures that the planet could no longer contain. The very foundations of life were about to be shaken not by a single cataclysm, but by a cascade of interconnected disasters. This was no mere reshuffling of species. This was the ultimate divestment of life, a planetary reset button pressed with brutal finality. We call it the Permian-Triassic extinction, but its ancient, raw power earned it a more somber title: the Great Dying. Imagine, if you can, the air itself turning toxic, vast reserves of carbon, locked away for eons in the Earth's crust, began to stir. Not a gentle awakening, but a violent eruption from the planet's molten heart. This was the age of the Siberian traps, immense volcanic provinces that spewed forth not just lava, but unimaginable quantities of greenhouse gases. These gases, carbon dioxide and methane, acted like a suffocating blanket, trapping heat and sending global temperatures soaring. The oceans, once a sanctuary, began to boil. Dissolved oxygen levels plummeted, creating vast, dead zones where life could no longer survive. But the heat and the poisoned air were not the only agents of destruction. The volcanic outgassing also released massive amounts of sulfur dioxide. When this mixed with atmospheric water, it rained down as acid, corroding landscapes and further poisoning terrestrial ecosystems. The world was literally burning from within and without. This era of unprecedented volcanism was the primary trigger. It unleashed a chain reaction, a perfect storm of environmental collapse. Whole ecosystems, so carefully built over millions of years, unraveled with terrifying speed. The synapsids, those hopeful early mammals, and countless other forms of life found themselves facing an insurmountable challenge. The fossil record from this period is stark. It shows a dramatic thinning of the strata, a period where the vibrant tapestry of life is reduced to mere threads. Entire families of organisms simply vanished, leaving behind not even a whisper in the geological record. It was a testament to the fragility of even the most successful adaptations when faced with such overwhelming planetary force. The sheer scale of this extinction event is difficult to comprehend. It is estimated that up to 96% of all marine species and 70% of terrestrial vertebrate species went extinct. Entire branches of the tree of life were pruned back so severely that they would never recover. This was the most profound biological crisis Earth has ever witnessed. And as the dust settled, as the suffocating gases began to dissipate, a new, starkly empty world was revealed. But even in this profound emptiness, life, as it always does, began to find a way. The question now is, what new forms would arise from the ashes? And when we look at the very foundations of these new burgeoning life forms, we must consider the dramatic shift that occurred in the atmosphere. The planet had purged itself. A silent, suffocating emptiness settled over land and sea. A canvas wiped clean by the Permian extinction's fiery hand. Yet life, stubborn and persistent, began to stir in the profound quiet. This was the dawn of the Triassic period, an age of slow, arduous recovery. The first few million years whispered with a fragile biosphere. Ecosystems were drastically simplified. Recovery was not a sudden bloom, but a gradual unfurling, like a desert flower pushing through cracked earth. The hardy pioneers were often the survivors least specialized, those capable of enduring extreme conditions. Among these tenacious survivors, new forms began to emerge. Not yet the titans we imagine, but small, agile creatures navigating a world still healing. We see the early archaeosaurs, a diverse group that would eventually give rise to many of the Triassic's dominant lineages. They were opportunistic, adapting to the still-forming niches. But evolution's slow march is rarely linear. The Triassic wasn't just about rebuilding. It was about redirection. The world was still fundamentally shaped by by the echoes of the great dying. The air itself held secrets, a lingering testament to the cataclysm. These secrets would soon give rise to a new kind of dominance, a reign that would echo through time. To understand how the very air we breathe became what it is, and how it paved the way for the giants, we must look at the subtle but profound shifts that defined the Triassic atmosphere. The Triassic period hummed with a unique atmosphere, still bearing the scars of the Permian's fiery breath, yet preparing for a new era. Conditions were often arid, with vast deserts stretching across Pangaea. Sunlight beat down relentlessly, shaping the resilient life that clung to existence. It was in this crucible of heat and scarcity that a lineage of reptiles began to distinguish itself. These were not yet the thunderous behemoths of legend, but smaller bipedal creatures. They moved with a swiftness and grace that set them apart from their sprawling ancestors. These early dinosaurs possessed a nascent evolutionary momentum. Their skeletal structures, though still primitive, hinted at an efficient bipedal gait that would become their hallmark. Their lungs, too, showed promising adaptations, a subtle foreshadowing of the efficient respiration that would fuel their future ascents. The world was still a mosaic of struggling life forms. Crocodilomorphs, relatives of modern crocodiles, also thrived, often occupying apex predator niches. Pterosaurs, the first flying vertebrates, began to take to the skies. But beneath this diverse tableau, the Archaeosaur lineage, from which the first true dinosaurs would spring, was quietly gaining an evolutionary foothold. We see the early signs of that distinct gait, that fundamental shift in skeletal architecture. The seeds of a coming reign were being sown, not with a bang, but with the steady beat of resilient hearts. To truly grasp the emergence of these first true dinosaurs, we must examine the geological whispers that mark their earliest footsteps. The Triassic period, a time of immense geological upheaval and life's tenacious resurfacing, was not to last. Toward its close, a series of catastrophic events began to unfold. The very earth seemed to groan under an immense pressure, a prelude to a cleansing that would reshape life's trajectory forever. Volcanic activity, on a scale unimaginable today, began to scar the planet. Gigantic fissures opened, spewing forth molten rock and a suffocating blanket of gases. These eruptions were not isolated events. They represented a widespread geological fever, a planetary tremor that set the stage for profound change. The atmosphere itself began to thicken with carbon dioxide and other volcanic byproducts. This trapped heat, leading to a significant global warming event. Oceans, too, were affected, their chemistry shifting, their ability to support diverse life forms diminishing. A slow suffocating began, not with water, but with air and heat. Life, which had so painstakingly re-established itself after the Permian extinction, now faced a new specialized and less adaptable creatures began to falter. Their intricate ecological niches, built over millions of years, crumbled under the relentless environmental assault. Yet, amidst this widespread decline, a subtle but significant pattern emerged. Life forms that were more generalized, more robust, or possessed adaptations for survival in harsher conditions began to gain an unexpected advantage. Their resilience, their ability to weather the storm, became their greatest asset. The question that hangs in the charged air of this era is not simply about extinction, but about the selective pressure that guided survival. What made some lineages vanish while others, poised on the edge of insignificance, found themselves on the precipice of a new dawn. To understand this selective clearing, we must delve into the very mechanisms of this catastrophic transition. The Triassic-Jurassic extinction event was not a singular moment, but a protracted agony. It ebbed and flowed, with pulses of heightened catastrophe, followed by periods of eerie calm. Yet the cumulative impact was devastating, wiping out an estimated 70–80% of all species on Earth. Marine life suffered immensely. Ammonites, belemnites, and many species of marine reptiles that had dominated the Mesozoic seas began to disappear. The intricate food webs that sustained these underwater realms fractured and collapsed under the relentless environmental stress. Terrestrial ecosystems were also profoundly altered. Entire plant families faced oblivion, their photosynthetic engines choked by atmospheric changes. Large amphibians and many reptilian groups, the dominant land dwellers of the Triassic, dwindled significantly. But within this great unraveling, a crucial shift was occurring. Certain groups, already exhibiting key adaptations, began to occupy the vacuum left by the fallen. The stage was being meticulously, albeit brutally, cleared for a new act in Earth's grand play. The extinction event acted like a cosmic winnowing. It removed the established players, the forms that had perhaps grown too specialized, too reliant on the Triassic's specific conditions. It was a reset button, a violent but necessary pruning of the evolutionary tree. To truly understand the ensuing age of dinosaurs, we must first dissect the very nature of this profound environmental reset. The air itself seemed to hum with a newfound dominance. Where once the Triassic had teemed with diverse reptilian forms, the Jurassic unfurled a tapestry woven with the threads of true giants. This was not a gradual ascent, but a bold declaration. The earth began to resonate with the weight of colossal footsteps. Sauropods, the long-necked behemoths, emerged as the undisputed rulers of the land. Their immense size was a testament to the evolutionary freedom granted by the post-extinction landscape. These creatures, with their towering frames and impossibly long necks, browsed the verdant canopies that had begun to flourish. They were living mountains, moving with a slow, deliberate grace that belied their power. The world belonged to them now, a verdant kingdom ripe for their consumption. But the age of giants wasn't solely defined by the gentle herbivores. The theropods, the predatory lineage that had survived the Triassic crucible, also began to grow in stature and ferocity. A new apex predator was beginning to stalk the plains. The ecological niches, once fractured and uncertain, were now solidifying. The abundance of plant life provided the fuel for immense herbivores, and these herbivores, in turn, sustained a new generation of formidable carnivores. It was a world shaped by scale and by a primal hunger. This era of unparalleled growth and dominance, however, was built upon the ashes of what came before. The quiet resilience of these emerging forms, their ability to capitalize on a planet reborn, hints at an even deeper planetary memory. To grasp the full scope of this awakening, we must turn our gaze to the skies, to the first tentative flights that would redefine the word giant forever. The vast, sprawling continents of the Jurassic provided the perfect canvas for a truly spectacular evolution in herbivorous life. Among the most awe-inspiring were the sauropods, creatures whose very name speaks of reptile feet, a deceptive simplicity for beings of such monumental scale. These were the gentle giants, the living mountains that reshaped the landscape with their browsing. Their long necks, some stretching astonishing lengths, allowed them to reach vegetation inaccessible to any other terrestrial animal. Imagine a forest canopy being systematically stripped bare by a slow-moving, living edifice. The sheer biomass of these sauropods demanded an equally vast supply of plant matter. They were moving ecosystems, their digestive tracts capable of processing immense quantities of foliage. But this prodigious appetite also meant they were profoundly sensitive to changes in their environment. Their existence, a testament to growth and abundance, was a direct consequence of earlier extinctions that had cleared the way. Yet, even within this era of giant herbivores, a subtle tension was brewing, a silent competition for resources that hinted at the next turning point in life's grand, unfolding narrative. To understand the pressures that shaped these titans, we must delve into the world of their predators. The Jurassic wasn't just a reign of herbivores, however peaceful it might seem from a distance. A shadow moved through those fern-choked forests and open plains. Allosaurus. This was the apex predator, a creature built for speed and power, a stark counterpoint to the slow, deliberate grace of the sauropods. Its skull was a marvel of evolutionary engineering, reinforced to withstand the crushing forces of its prey. Serrated teeth like daggers, lined jaws that could open impossibly wide. Allosaurus was not a hunter that relied on brute force alone. It was a calculated predator, likely using its powerful legs to deliver disabling blows before closing in for the kill. The presence of such formidable hunters played a crucial role in the evolution of their prey. Defensive structures, like the armor of stegosaurs or the sheer immensity of the sauropods, were not mere happenstance. They were direct responses to the constant threat posed by carnivores like Allosaurus. Imagine the landscape. A herd of sauropods, a moving landscape of flesh, grazing placidly, but always on the periphery, the watchful eyes of Allosaurus. The air would thicken with a primal tension, a scent of fear, and the thrill of the hunt. This balance of predator and prey, this ancient dance of life and death, was a fundamental force shaping Earth's history. But the very success of these apex hunters also sowed the seeds of their future challenges. A story that leads us to the cataclysmic events of the Cretaceous, the age of dinosaurs' end. The land teemed with giants, a vibrant tapestry of reptilian life. Yet beneath the surface, an equally spectacular drama unfolded. The Jurassic seas were not merely watery expanses. They were vast, dynamic kingdoms dominated by a different kind of reptilian marvel, marine reptiles. These were not the clumsy amphibians of earlier epochs. These were creatures sculpted by the ocean's currents, evolved for a life spent in the embrace of the deep. Their forms were streamlined, their limbs adapted into powerful flippers, perfect for navigating the vast blue. Among them, the ichthyosaurs swam like torpedoes, their names meaning fish lizards. They bore an uncanny resemblance to modern dolphins, a striking example of convergent evolution. Their eyes, large and keen, were built to pierce the dim light of the depths, searching for prey. But the oceanic world was not solely for agile hunters. The plesiosaurs, with their long necks and barrel-shaped bodies, adopted a different strategy. They were the patient stalkers, their necks allowing them to reach into crevices and grasp unsuspecting prey, their bodies moving with a slow, powerful rhythm. And then there were the pliosaurs, the true titans of the Jurassic seas. These were the apex predators of the water, their massive jaws and formidable teeth, capable of dispatching even the largest ichthyosaurs. Their dominion was absolute, a testament to the power of adaptation. These marine reptiles were more than just animals. They were living embodiments of the ocean's untamed spirit. Their existence was a constant cycle of hunting and evasion, a silent, ancient ballet played out in the sun-dappled shallows and the inky blackness of the abyss. But the dominance of these scaled rulers was not eternal, and their eventual decline would pave the way for new masters of the waves, a story that unfolds as we transition to the dawn of the Cretaceous period. The age of the great marine reptiles began to wane, a slow fade across the vast blue canvas of Earth's ancient oceans. But as these scaled rulers receded from their zenith, a new chapter was quietly unfolding on the continents, a transformation that would forever alter the face of terrestrial life. This was the dawning of the Cretaceous period, a time of burgeoning diversity and a profound shift in the very air we breathe. On land, the ancient cycads and ferns still held sway, but a subtle revolution was brewing in the undergrowth. Small, unassuming pioneers of a new botanical order were beginning to unfurl their petals and spread their seeds. These were the first flowering plants, a lineage that would eventually paint the world in a riot of color and fragrance. Their whispers of innovation began in this era, a quiet promise of the vibrant tapestry to come. It was a world teetering on the edge of abundance. The land was becoming a more verdant place, a richer habitat for creatures of all sizes. And in this evolving landscape, a new kind of predator began to emerge, a creature that would capture the imagination for millennia to come. The tyrant lizard king. These were the early ancestors of the Tyrannosauridae family apex predators, whose very presence commanded respect. Their frames were still developing, their stature not yet the colossal height we often envision, but the primal power was undeniable. Their jaws, even in these nascent forms, hinted at the bone-crushing might that would define their legacy. The rhythm of life was changing. The earth was breathing deeper, its flora diversifying, and its fauna reaching new heights of specialization. The ground began to tremble with the footsteps of these nascent giants, a prelude to the thunderous rain that would define the latter half of this remarkable period. The seeds of change were sown, and the Cretaceous was ready to bloom, a testament to Earth's ceaseless capacity for reinvention. To understand the full scope of this vibrant rebirth, we must delve deeper into the ecological shifts that accompanied the rise of the flowering plants and the ultimate reign of the tyrannosaurs. The shadow of the Tyrannosaurus rex looms large in our collective consciousness. More than just a name, it represents the pinnacle of predatory evolution on land, a creature sculpted by millions of years of trial and error. Its very existence speaks to a world that had, by the late Cretaceous, become a stage for some of Earth's most formidable actors. Imagine the Texas landscape, dotted with cycads and ferns, a place where the air itself felt thick with the hum of life. It was here, in this ancient and vibrant ecosystem, that the Tyrannosaurus rex took its first steps, a nascent king surveying its domain. But the early iterations of this lineage were not yet the iconic giants. They were smaller, leaner, perhaps more agile. These early tyrannosaurs were already masters of their environment, honing the predatory skills that would eventually lead to their most famous descendant. Their senses were sharp, their pursuit relentless. They were the embodiment of raw, untamed power, a force of nature in their own right. Long before the T-Rex became a legend, the development of their powerful jaws and bone-crushing bite was not a sudden event. It was a gradual refinement, a biological imperative driven by the need to secure scarce resources and dominate rivals. Each evolutionary step was a testament to the relentless pressure of survival, a slow, deliberate shaping of a future titan. And as these early predators perfected their craft, the stage was being set for an unparalleled dominance. To truly grasp the essence of the Tyrannosaurus rex, we must first understand the evolutionary pressures that shaped its ancestors. The world, once dominated by the stark greens of ferns and conifers, was about to be painted with an explosion of color and complexity. A silent revolution was brewing, not in the roar of predators, but in the delicate unfurling of petals. This was the dawn of the angiosperms, the flowering plants, a botanical upheaval that would fundamentally alter the Earth's ecosystems. Before this era, the plant kingdom was a simpler place. Forests were made of giants like cycads and ginkgos, their reproductive strategies ancient and slow. But then, something new began to emerge, a subtle but profound shift in the very architecture of life. It started with small changes, the development of enclosed seeds, and then the breathtaking innovation of the flower. These early flowers were likely modest, perhaps even ephemeral, but their impact was anything but. They represented a new way for plants to interact with their environment, a strategy that would prove incredibly successful. This wasn't just about reproduction. It was about partnership, about forging new alliances in the grand theater of life. The development of flowers was a masterful evolutionary gamble. It offered an enticing reward, nectar and pollen, to attract pollinators. This created a feedback loop where the plants evolved to better attract their partners, and the insects, birds, and other creatures evolved to better exploit these new food sources. But the true profundity of this botanical revolution lay beneath the surface. In the very way these plants spread their seed, it was a strategy that allowed for speed and diversity, a departure from the slow, wind-borne dispersal of older plant forms. The emergence of these new plant forms began to reshape the landscape, introducing a vibrant new tableau. What began as a whisper of change in the undergrowth was about to become a dominant chorus, creating habitats unlike any seen before. To understand the fullness of this botanical shift, we must look closer at the intricate dance that began with the first blossoms, a prelude to the vibrant tapestry of the Cretaceous. The very ground beneath us began to stir and separate. For eons, the vast supercontinent of Pangaea had held sway, a colossal landmass shaping the planet's climate and life. But the deep forces within the Earth, relentless and patient, were beginning their work. Slowly, imperceptibly at first, cracks began to appear. These were not superficial fissures. They were the first hints of a colossal unraveling. Molten rock, born from the planet's fiery heart, surged upwards, widening the nascent rifts. The immense weight of Pangaea, once a symbol of unity, now became became a force driving its own dismemberment. Continents that had known only each other for incomprehensible stretches of time started to drift apart. Imagine ancient mountain ranges, once connected, now slowly yielding to the immense pressure of the separating crust. This was the genesis of new oceans, vast bodies of water born from the tearing of the land. The breakup was not a single violent event, but a protracted process, a slow-motion ballet of geological forces. As the land masses pulled away from each other, new coastlines emerged, landscapes were fractured, and fundamental changes to global weather patterns began to unfold. This grand tectonic reshuffling was setting the stage for entirely new biological frontiers. This immense geological drama, the breakup of Pangaea, did not occur in isolation. It was a process deeply intertwined with the evolving biosphere, the newly forming oceans, and the altering continental configurations began to influence everything from ocean currents to atmospheric circulation, subtly guiding the course of life. And to truly grasp the magnitude of these changes, we must now consider the first echoes of the great reptilian age that would soon dominate the emerging continents. The very air seemed to thicken with an unseen dread. A celestial visitor, a harbinger from the profound darkness between stars, was on a collision course with our world. This was no gentle arrival, no slow embrace, but a swift, cataclysmic plummet. For millennia, this colossal body had journeyed, a silent wanderer across the cosmic ocean. Now its trajectory was set, its destination Earth. The immense kinetic energy it carried promised an impact of unimaginable force. As it pierced the atmosphere, a searing inferno ignited. The sky itself seemed to burn, a fleeting, terrifying spectacle before the inevitable. This was the moment life on Earth would be irrevocably altered. The impact itself was a wound torn into the planet, a blinding flash, brighter than 1,000 suns, preceded a shockwave that ripped through the crust. Vaporized rock and molten debris were flung outwards, a fiery rain painting the heavens. The immediate aftermath was devastation on a scale that defies simple comprehension. Firestorms raged, engulfing continents. Tsunamis, born from the ocean's violent displacement, surged inland, wiping coastlines clean. Earthquakes, far exceeding any recorded tremor, shook the very foundations of the world. But the most profound alteration was not immediate. It was the insidious shadow that followed, a suffocating blanket cast over the sun. Dust and ash, a celestial shroud, choked the atmosphere, plunging the world into an extended, suffocating twilight. Photosynthesis faltered. The very base of the food chain collapsed. This darkness, this chilling absence of light and warmth, was the true enemy. It was the silent killer that brought an end to an era. The reign of the mighty dinosaurs that had lasted for ages was about to be extinguished by this cosmic ultimatum. And to understand the true consequence of this darkened world, we must look at the stark silence that fell upon the land and the fragile new beginnings that struggled to emerge in its wake. The sky, once a canvas of vibrant blues and sunlit clouds, turned a permanent, sickly gray. A perpetual twilight descended, a suffocating embrace that stole the warmth of the sun. The vibrant greens of ancient forests faded, replaced by the stark browns of dying flora. Life, so abundant and diverse, began to falter and then to cease. The great herds of herbivores, their food sources dwindling, grew weak and perished. The predators that hunted them, finding their prey gone, faced the same grim fate. A chilling silence began to spread across the land. The sheer scale of this extinction is hard for our minds to grasp. It was not a single event, but a cascade of consequences, each more devastating than the last. The impact was the trigger, but the subsequent environmental collapse was the true executioner. Beneath the suffocating dust, the deep roots of life clung to existence. Small creatures, adapted to burrowing or to the sparse resources of this new world, survived. These were the forgotten, the overlooked, the ones who would inherit a planet stripped bare. Their quiet persistence was a whisper of hope in the deafening silence. The age of giants had come to an abrupt and violent end, not by a slow decline, but by a celestial hammer blow. The world was reshaped in fire and shadow, and the familiar rhythms of life were broken. But even in this profound darkness, the story was not truly over. To witness the first fragile stirrings of a new dawn, we must examine the quiet emergence of mammals in the aftermath of the Great Dying. The Paleogene period, a name that whispers of ancient beginnings, marks the dawn of a new era. It is the age of mammals, a time when these resourceful creatures, once relegated to the shadows, began their slow, deliberate ascent. Imagine a world still scarred, its landscapes reshaped by the cataclysm that preceded it. The air itself carried a different weight, the silence broken only by the rustle of smaller beings. These were not the colossal beasts of the Mesozoic. These were the survivors, the adaptable, tiny shrew-like ancestors, rodent-sized creatures, and early primates, their lineage tracing back to the very edge of extinction. They moved through a world that had been cleared, a blank canvas awaiting a new masterpiece. The extinction event had removed the dominant players, the great reptiles that had ruled for eons. This created ecological niches, vast empty spaces in the grand tapestry of life. A silent invitation was extended to those who could seize it. The earth offered fertile ground for a different kind of domination, one built not on sheer size, but on adaptability and a more complex kind of intelligence. The fossil record offers us glimpses of this transition, fragmented narratives etched in stone. We see the gradual diversification, the slow unfolding of mammalian forms. Each new discovery, Each newly identified bone is a clue to this unfolding drama. The question that arises, a persistent hum beneath the surface of our understanding, is how these small, seemingly insignificant creatures managed to seize control. What intrinsic qualities allowed them to flourish in the wake of such profound devastation? To understand this remarkable revival, we must delve into the very essence of what makes a mammal and the subtle advantages they possessed. The world breathed again, but it was a different breath, a quiet one, filled with the scurrying of small things. These early mammals were not the kings of the ancient world. They were the shadows, the survivors who had weathered the storm. Small, often no larger than a modern-day shrew or a small rodent, they hid in the undergrowth, their existence a testament to resilience. They possessed a unique set of evolutionary gifts. Warm-bloodedness allowed them to be active in cooler temperatures, to venture out when the giant reptiles were sluggish. This gave them an edge, a flexibility that cold-blooded creatures lacked. But perhaps their most profound advantage lay in their reproduction. Mammals gave birth to live young, nurturing them with milk produced from specialized glands. This parental care, this investment in the future generation, was a slow burn of evolutionary advantage. It meant that young mammals were not left to fend for themselves from birth. They were protected, fed, and guided, learning the ways of the world from their mothers. This fostered a more complex social behavior and a greater capacity for learning. These were not the roaring titans of a lost age. These were meticulous planners, opportunistic foragers, and devoted parents. They were the seed from which a new epoch would grow. But how did this seemingly fragile beginning lead to the astonishing diversity of mammals we see today? The answer lies in a gradual evolutionary dance, a slow and deliberate unfolding of form and function. To truly grasp this, we must look closer at the very anatomy that defined these early survivors. The age of the great reptiles had ended, leaving a world forever changed. For a time, the remnants of that era continued to roam, but their dominion was broken. Into this altered landscape stepped the quiet inheritors, the small, furry creatures that had endured. Yet even their survival was not without its challenges. The earth itself continued its restless cycle of change, and a profound shift was on the horizon, a period of intense warming, the likes of which had not been seen for epochs, was about to grip the planet. This was the Paleocene-Eocene thermal maximum, a sudden and dramatic spike in global temperatures. Imagine the world, already reshaped by extinction, now experiencing a fever. The lush forests began to steam. The shallow seas grew unnervingly warm. It was a crucible, a test of adaptation born not from a single cataclysm, but from a slow, pervasive heat. The question arises, how did creatures so seemingly ill-equipped for such extremes not only survive, but thrive? The answer, I suspect, lies not just in their physical forms, but in their innate behaviors. The mammalian lineage, even in its nascent stages, possessed a certain adaptability. Their warm-blooded nature, a trait already setting them apart, might have been their first line of defense. It allowed them to tolerate a wider range of temperatures, to seek out cooler refuges, or perhaps to even exploit the newfound warmth in ways their colder-blooded ancestors could not. But this warming was extreme, pushing the boundaries of even this advantage. The evidence etched in the rock layers shows a dramatic shift. A layer, distinct and undeniable, speaks of this global fever. It's a temporal scar, a testament to a planet under immense thermal stress. And within this fiery epoch, a new chapter in mammalian evolution began to write itself, not through conquest, but through a subtle, yet powerful biochemical adaptation. To understand how they navigated this era of scorching heat, we must delve into the very chemistry of life itself, exploring the secrets of their metabolic resilience. The Eocene epoch, a vast expanse of time stretching for some 20 million years, dawned in the aftermath of a planet-altering fever. The world, seared by a dramatic spike in global temperatures, began to settle into a new, warm rhythm. Imagine continents adrift, still settling into their modern configurations, fringed by shallow, balmy seas. It was an era of profound warmth, a greenhouse world far removed from the cooler climates that would later define Earth's autobiography. Forests, dense and vibrant, carpeted much of the land masses, their leaves reaching towards a sun that seemed to shine with an unending intensity. But this pervasive warmth was not a passive backdrop. It was an active force, shaping the very fabric of life. The diversification of life during the Eocene is a testament to this environmental pressure. New forms emerged, thriving in conditions that might seem alien to us now. The mammalian lineage, already established, experienced an unprecedented surge in variety. This was not merely a chance proliferation, but a calculated expansion into ecological niches that had been reshaped by the preceding thermal events. You can almost feel the planet exhaling a new breath, a slow, warm exhalation that encouraged growth and innovation. And as these new forms took hold, a different kind of story began to unfold in the deep strata. It's a story not of survival by brute force, but by an intricate dance with biochemistry. The question that hangs in the humid air of this epoch is, what subtle shifts at the cellular level allowed these creatures to flourish when the planet itself seemed to be holding its breath in the heat? To answer this, we must examine the fundamental building blocks of their existence, the very engines that powered their ascent during this golden age of mammalian expansion. The balmy seas began to recede, a subtle shift that hinted at a grander transformation. The Eocene's feverish warmth, which had nurtured such vibrant innovation, was slowly, almost imperceptibly, beginning to ebb. This wasn't a sudden plunge into ice, but a gradual cooling, a softening of the planet's embrace. As the heat lessened, the very architecture of the terrestrial world began to change. The dense, humid forests that had dominated for so long started to yield. Their ancient reign was challenged by new contenders, plants that thrived not in perpetual damp heat, but in conditions that allowed for more open spaces and drier spells. This encroaching coolness, this gentle nudge away from the greenhouse, was the quiet architect of a new landscape. It was a shift that invited, perhaps even necessitated, a different kind of biological response. The world was not yet an ice age, but it was no longer the Eocene's steamy cradle. The grasslands, those vast carpets of resilience, began to spread. They were the vanguard of this new climatic regime, their roots anchoring themselves in soils that were becoming less saturated, more exposed to the changing atmospheric currents. This unfurling of open plains set the stage for a profound evolutionary drama. And as these grasslands expanded, so too did a particular group of animals find themselves perfectly poised to exploit this expanding frontier. Their lives became intrinsically linked to the rhythm of the seasons, to the waxing and waning of sunlight on open savannas. But this new world of grass and changing temperatures presented its own unique challenges, and the question remains: what subtle adaptations allowed certain lineages to not just survive, but to truly thrive in this emerging age of open lands and cooler skies? To understand this, we must turn our gaze to the very structure of their bodies and the shifting pressures of their environment. The very ground beneath our feet began to settle into familiar shapes during this era. The colossal tectonic ballet that had sculpted the planet for eons showed signs of nearing its grand finale, at least in terms of continental configuration. These vast landmasses, the architects of global climate and biodiversity, were largely finding their places. The mighty mountain ranges, born from violent collisions, continued their slow erosion, their stony shoulders bearing witness to time itself. But it was the placement of the continents, their relative positions and proximities, that cast long shadows over the planet's future. These were not the chaotic, shifting plates of earlier ages. This period saw the Atlantic Ocean deepen, a placid expanse widening as the Americas steadily drifted westward. Africa continued its northward embrace of Europe, pushing up the Alps and forging the Mediterranean Sea in a lingering, majestic embrace. India's relentless march had already created the Himalayas, a stark and breathtaking testament to geological force. Even the island continents, like Australia, were charting their course, albeit at a more glacial pace. The arrangement was becoming recognizable, a blueprint for the world we inhabit today. This continental stability, this nearing of modern geography, was more than just a reshaping of the physical world. It was the setting of a stage where new ecological narratives could begin to unfold. But as the continents found their modern forms, what deeper, more subtle shifts were occurring within the Earth's very core and mantle that would continue to influence life's trajectory. We must look to the deep internal rhythm of our planet to understand the forces that truly shaped this emerging world. The Miocene epoch dawns not with a roar, but with a profound and steady hum. The stage is set. The continents are largely in their modern configurations, and a familiar rhythm begins to shape the continents and oceans. The Atlantic is a vast, growing child of divergence, and the Mediterranean, a complex, shrinking echo of ancient collisions. This stability, this comforting geological familiarity, allows for a different kind of drama to unfold. Life, too, begins to settle into patterns we can recognize. The great mammalian radiation, a burst of evolutionary innovation that began in the prior epoch, continues its vibrant work. It is as if the very architecture of the Earth has stabilized enough to allow its inhabitants to explore every available niche, to diversify with an exhilarating freedom. This is a time of great herds on the expanding grasslands, of new predators testing their strength, of intricate food webs weaving themselves across landscapes. The world is becoming more open, more accessible to the creatures that walk, crawl, and fly. Think of the vast plains that begin to dominate interiors of continents, the forests that flourish in wetter regions, the slow, constant reshaping of coastlines. Each environment offers a unique invitation to life, and life, in its infinite ingenuity, answers. But beneath this surface flourishing, this unfolding tapestry of familiar life, what subtle environmental pressures were driving this diversification? What shifts in climate, unseen by the mammals themselves, were sculpting their evolving forms? To truly grasp the Miocene's vibrant pulse, we must examine the slow breath of Earth's climate, the Pliocene epoch, an era stretching from about 5.3 to 2.6 million years ago, opens onto a world that feels increasingly, strikingly familiar. The continents have largely settled into their modern configurations, the grand ballet of plate tectonics slowing to a more stately, predictable rhythm. This era is often heralded as the dawn of hominins, the period when our own lineage began to diverge and thrive. It is a time when the Earth's climate began a gradual cooling trend, a subtle but significant shift that would echo through the millennia. Ice sheets, though not yet as vast as in later epochs, began to expand at the poles, influencing ocean currents and atmospheric patterns. This slow transformation of the global thermostat provided a new set of challenges and opportunities for the life that inhabited the planet. As the Miocene's vibrant biodiversity continued to flourish, new pressures emerged, subtly altering the evolutionary course. The forests that had dominated earlier eras began to recede in some regions, replaced by expanding savannas and grasslands. This shift created new ecological frontiers, favoring creatures adapted to open environments and the challenges of a more variable climate. Within this changing landscape, a remarkable story unfolded in the Great Rift Valley of Africa and in other scattered pockets across the continent. The evolutionary experiment that would eventually lead to Homo sapiens took root. These early hominins, our distant ancestors, were emerging from the shadows of the forest canopy. They were beginning to walk upright, a profound adaptation that would reshape their relationship with the world. This bipedalism freed their hands, allowing for the manipulation of tools and objects in ways never before possible. It also offered a new vantage point from which to survey their surroundings, to observe the subtle shifts in the savanna, and to track the movements of game. But what exactly were the environmental cues, the subtle atmospheric whispers and geological nudges that encouraged such a radical shift in locomotion? What unseen forces within the expanding grasslands were prodding these creatures towards a more upright existence, a posture that would define our future? To understand the genesis of our own kind, we must delve into the very breath of the Pliocene atmosphere. The faint warmth of the Pliocene began to cool, a subtle shift that would soon cascade into something far more dramatic. The Earth, which had enjoyed a relatively stable climate for millions of years, started to feel a new kind of pressure. Deep within the planet, tectonic plates continued their slow dance, rearranging continents and ocean currents, subtly rerouting the planet's grand thermal engine. But the most profound changes were brewing in the atmosphere. The composition of the air itself was changing, becoming less efficient at trapping the sun's warmth. The delicate balance that had sustained lush forests and sprawling savannas was tilting, not with a sudden lurch, but with a slow, irresistible descent. The first whispers of this change were felt at the poles. Snow and ice, which had always been seasonal visitors, began to linger. They did not melt away with the summer sun as they once had. Instead, they deepened, year after year, century after century. This growing whiteness reflected more sunlight back into space, a feedback loop that amplified the cooling. And then they advanced, not with the roar of a thunderstorm, but with the silent, inexorable creep of a glacier. Vast sheets of ice, kilometers thick, began to spread from the polar regions. They advanced southwards, covering ancient landscapes, grinding mountains into dust, and reshaping the very continents. This was the dawn of the Pleistocene epoch, an era defined by the grand rhythm of the ice ages. The glaciers were not static, however. They advanced and retreated over tens of thousands of years, creating cycles of intense cold and periods of relative thaw. These shifts dramatically altered sea levels, exposing land bridges that allowed species to migrate, while at other times, submerging vast coastal plains. The world became a more dynamic and, in many ways, a more challenging place. But what were the subtle atmospheric triggers, the precise orbital nudges that initiated these colossal ice sheets? What unseen atmospheric composition changes allowed ice to persist and then advance across entire continents? A phenomenon that would define the very fabric of life for millennia to come. To truly grasp the scale of these glacial epochs, we must examine the delicate dance of Earth's orbit. The Earth itself began to move in a slow, grand waltz, a celestial ballet that dictated the fate of ice and sea. These weren't random shifts, but predictable patterns etched into the geometry of our planet's journey around the sun. The tilt of Earth's axis, the shape of its orbit, the wobble of its spin, these factors combined in a complex interplay known as the Milankovitch cycles. These cycles operate on timescales far beyond human experience, unfolding over tens of thousands of years. When the Earth's orbit is more elliptical, bringing us closer to the sun at certain points, and its axial tilt is more pronounced, allowing for more extreme seasonal variations, the conditions become ripe for glaciation. The summers in the high latitudes might be warmer, but if the winters are colder and the snow accumulation exceeds the summer melt, ice begins to build. The ice sheets, born from persistent snowfall, did not merely sit passively. They were dynamic forces, carving valleys and shaping landscapes with an unimaginable power. As they advanced, their immense weight compressed the ground beneath them, and their abrasive ice scraped away rock and soil, leaving behind U-shaped valleys and vast plains of till. Yet these ice ages were not permanent. The same orbital rhythms that initiated them also held the key to their eventual retreat. As the Earth's orbit became more circular and its axial tilt lessened, the summers became more effective at melting the accumulated ice. This gradual warming allowed the glaciers to recede, exposing land that had been buried for millennia. But the precise balance between snowfall and melt, the atmospheric composition that favored ice accumulation versus its dissolution, remains a profound question. To unravel this delicate balance, we must look deeper into the very air and its ancient secrets. The ice retreated, and a new chapter began to unfold, not just for the land, but for the life that would reclaim it. As the frozen grip loosened, the world emerged, damp and vibrant, ready for the rise of giants. Imagine a world where the ground itself seemed to tremble with each step, where creatures of impossible scale walked beneath a sky that felt somehow smaller. These were the megafauna, the undisputed titans of an age not so distant. Mammoths with their shaggy coats and immense curved tusks browsed on the tundra. Ground sloths, larger than rhinoceroses, moved with a slow, deliberate grace through ancient forests. Saber-toothed cats, their canine teeth like gleaming daggers, prowled in the shadows. Apex predators in a realm of colossal prey. These creatures were more than just large animals. They were integral to the ecosystems they inhabited, shaping landscapes through their grazing and their migrations. Their sheer presence dictated the evolutionary paths of countless other species. From the grasses they consumed to the smaller predators that followed in their wake. They were the embodiment of a wild, untamed earth, a testament to life's boundless capacity for grandeur. But the reign of these giants was not eternal. Their disappearance, as mysterious and profound as their existence, left a void that echoes even today. What force could fell such immensity? What shift in the earth's subtle rhythms led to their silence? To understand this fading, we must consider the profound impact of the beings who would eventually inherit their world, and the peculiar nature of their own arrival. The great titans of the Pleistocene, their immense forms etched into the very memory of the earth, eventually yielded to forces we are only beginning to comprehend. Their fading left a spectral presence, a reminder of scales of life that once dominated the land. But as these giants receded, the stage was being set for a different kind of emergence, one that would redefine the planet's future in ways far more subtle, yet ultimately more profound. It is a story whispered in fossils, coded in genetics, a slow unfolding over millions of years. We speak now of our own beginnings, the deep roots of Homo sapiens. To grasp humanity's place in the grand tapestry of life, we must journey back to the ancient cradle of our lineage. Think not of the familiar bipedal form, but of creatures far more primitive, navigating a world shaped by forces that seem alien to us now. These early hominins, our distant ancestors, were products of their unique environments, their survival a constant dance with the evolving earth. Their story is not one of sudden appearance, but of gradual adaptation, a slow unfolding of traits that would eventually lead to self-awareness. We see the first stirrings in the African savanna, a landscape of stark beauty and relentless challenge. Here, the pressures of predation and resource scarcity began to sculpt a new path for a specific branch of primate evolution. The very ground beneath their feet, the air they breathed, the changing climate, all played their part in this grand, slow-motion transformation. What were the earliest flickers of intelligence that set our kind apart? It is a question that probes the very essence of consciousness. We look to the fossil record, to the subtle shifts in skeletal structure, searching for the first hints of the traits that would one day define us. The upright stance, the changing hand, the ever-increasing cranial capacity, each a quiet revolution within the slow breath of deep time. To truly understand our origin, we must look beyond the individual species and consider the intricate web of life that supported them. The changing flora, the the migratory patterns of other animals, even the geological forces that reshaped continents, all were integral to the story of Homo sapiens. The environment was not merely a backdrop. It was an active participant, a relentless sculptor of form and function. It is in this dynamic interplay, this ancient dialogue between life and land, that we begin to trace the faint, yet undeniable line that leads to us. But the landscape of our genesis is far from simple. Within this unfolding narrative, a crucial development began to emerge, a fundamental shift that would alter the trajectory of all life on Earth. To unravel this pivotal change, we must turn our gaze to how our earliest ancestors began to interact with their world and the startling implications of their growing connection. The Holocene epoch, the time in which we now find ourselves, is a remarkable pause. It is an interglacial period, a relative warmth that has allowed civilizations to blossom and life to flourish in ways that were unimaginable during the brutal grip of glacial ages. This extended warmth is not a permanent state, but a gentle sigh between ice storms stretching across millennia. We have become accustomed to its stability, to predictable seasons, and a relatively consistent climate. But this epoch, stretching back some 11,700 years, is a delicate balance. It is a chapter written in a unique atmospheric composition, a subtle yet profound alteration in the very air we breathe. Within this epoch, a new dynamic began to weave itself into the fabric of existence. Life, no longer solely focused on survival against overwhelming cold, began to explore new avenues. The landscapes, softened by receding ice, invited expansion and innovation. It is here, in this era of relative calm, that we witness a profound shift in the relationship between humanity and the earth. A connection more potent than any before started to take root, changing not just our environment, but our very nature. This growing influence, this emergent power, leads us directly to the dawn of a new geological consideration. The Holocene, this period of gentle warmth, provided the canvas upon which modern ecosystems were painted. Life, freed from the crushing weight of ice sheets, began to diversify and specialize. The vast, simplified landscapes of glacial times, scoured clean by ice, slowly gave way to intricate mosaics of forest, grassland, and wetland, each with its own cast of inhabitants. This was a time of dynamic equilibrium. Species that had survived the harshness of the ice ages found new niches to explore, while others, perhaps more sensitive to the changing conditions, saw their numbers dwindle or their ranges contract. The air itself, gradually accumulating certain gases, began to hold warmth, allowing for a greater abundance and variety of plant life. But this flourishing was built on a fragile foundation. The interconnectedness of these newly forming ecosystems meant that a change in one part could ripple outwards, affecting many others. rise and fall of populations, the migration of species, the subtle shifts in soil composition, all these played their part in creating the complex tapestry of life we recognize today. You might feel the interconnectedness too, a sense of belonging to something larger, a web of life that supports and sustains. Yet beneath this sense of harmony, a new force was stirring, one that would soon begin to rewrite the rules of this delicate balance. And to understand the forces that truly shaped these modern ecosystems, we must first delve into the profound atmospheric shifts that accompanied their formation. The air, once a passive stage for geological drama, has become an active player, its very composition altered by a new force. This force, stemming from a single species, has begun to question the natural order. We call this epoch the Anthropocene, a period where the footprint of humanity is not a fleeting trace, but a geological signature. Have we, in our relentless pursuit of progress, truly reshaped the planet on a scale comparable to ice ages or asteroid impacts? The evidence is accumulating, layer by layer, in the very strata of our world. Consider the silent testimony of the soil, now laced with plastics and industrial pollutants, or the oceans, absorbing the excess carbon we pump into the atmosphere. This is not merely a story of human ingenuity. It is a profound encounter with consequence. The signals are subtle at first, like a whisper beneath the roar of industry, but they grow louder with each passing year. The question lingers: have we crossed a threshold, irrevocably altering the planet's trajectory? And to fully grasp the magnitude of this seismic shift, we must now examine the very markers left by this new era. We speak of time as a river, flowing relentlessly forward. But how do we measure its vastness? The unfathomable stretches before us and behind us. Geologists have devised scales, immense frameworks to map the epochs of Earth's existence. These scales are not arbitrary divisions. They are etched into the very rocks, each layer a page in a book millions of years old. Imagine the Earth's history laid out like the rings of a colossal tree. Each band represents a distinct era, a period characterized by unique geological events: the rise and fall of great mountain ranges, the ebb and flow of ancient seas. These are not simple timelines. They are intricate tapestries, woven with the threads of continental drift, volcanic outpourings, and the slow, patient work of erosion. Understanding these geological timescales is like learning a new language, one spoken by the planet itself. It allows us to perceive patterns, to see the grand cycles of change that have shaped our world. But grasping its immensity requires a shift in perspective, a willingness to let go of human-centric notions of time. It's in recognizing these deep time markers that we begin to truly comprehend the forces at play. And to comprehend these scales, we must first understand the fundamental units that define them. We speak of time as a river, flowing relentlessly forward. But how do we measure its vastness? The unfathomable stretches before us and behind us. Geologists have devised scales, immense frameworks to map the epochs of Earth's existence. These scales are not arbitrary divisions. They are etched into the very rocks, each layer a page in a book millions of years old. Imagine the Earth's history laid out like the rings of a colossal tree. Each band represents a distinct era, a period characterized by unique geological events. The rise and fall of great mountain ranges, the ebb and flow of ancient seas. These are not simple timelines. They are intricate tapestries, woven with the threads of continental drift, volcanic outpourings, and the slow, patient work of erosion. Understanding these geological timescales is like learning a new language, one spoken by the planet itself. It allows us to perceive patterns, to see the grand cycles of change that have shaped our world. But grasping its immensity requires a shift in perspective, a willingness to let go of human-centric notions of time. It's in recognizing these deep time markers that we begin to truly comprehend the forces at play. And to comprehend these scales, we must first understand the fundamental units that define them. For centuries, the age of the Earth remained a profound mystery. The sedimentary layers offered clues, a stratigraphic record that hinted at immense durations, but a precise measure eluded us. We could count rings in a tree or layers in ice, but the Earth itself seemed to possess no such obvious clock. The secrets were locked within its deepest structure, within the very atoms that compose its rocks. It was a silence that echoed through the eons, a fundamental unknown. Then a subtle whisper emerged from the heart of matter. Scientists began to observe that certain elements, unstable and restless, were not fixed, but were slowly, predictably transforming. This transformation, this decay, was not random. It proceeded at a constant, unwavering rate, independent of heat, pressure, or chemical environment. It was a cosmic metronome, ticking in the darkness of the Earth's crust. This process, known as radioactive decay, offered a remarkable insight. Imagine a clock where the ticking rate never changes, no matter the conditions. Each radioactive element contains within it a parent isotope, a kind of unstable grandparent, and as it decays, it transforms into a stable daughter isotope, the grandchild. By measuring the ratio of parent to daughter isotopes within a rock sample, and knowing the rate of decay, geologists could count the ticks. It was like finding a hidden stopwatch embedded in ancient minerals. This discovery was revolutionary. It provided a physical basis for dating, a way to anchor the geological timeline, not just in relative sequences, but in absolute numbers. Suddenly, the vast, seemingly immeasurable gulfs of time began to yield their secrets. We could move beyond simply knowing that one layer was older than another, to knowing how much older. But the power of this atomic clock was not immediately apparent, and its application required careful calibration. To truly unlock Earth's chronology, we had to understand these decay rates with incredible precision, and this led us to the concept of half-life. The half-life of these elements, the time it takes for half of a parent isotope to transform into its daughter, became the fundamental unit of our geological clock. It is a concept of immense patience, of processes unfolding on scales that dwarf human comprehension. Some radioactive isotopes have half-lives measured in billions of years, others in mere seconds. But for dating the ancient rocks of our planet, we rely on those with half-lives measured in hundreds of millions, or even billions of years. These slow, steady transformations, invisible to the naked eye, were the keys to unlocking the deep past. This understanding of radioactive decay fundamentally reshaped our perception of Earth. It revealed a planet not static, but in a perpetual state of flux, a dynamic system where time itself could be measured through the very substance of the rocks beneath our feet. It was a profound shift, moving us from an Earth of unknown antiquity to one with a precisely quantifiable history. Yet even with this powerful new tool, the story of Earth's enduring presence was far from complete. The very rocks that held these radioactive clocks were themselves part of a grander, more cyclical narrative. They spoke of constant renewal, of a planet that endlessly rebuilds itself from its own ancient foundations. This is the story of the rock cycle. The rock cycle is perhaps the most eloquent metaphor for Earth's persistent spirit. It describes the constant transformation of rocks from one type to another: igneous, sedimentary, and metamorphic. Imagine molten rock, magma, cooling and solidifying into igneous rocks. These can then be broken down by wind and water, their fragments accumulating to form sedimentary layers. Extreme heat and pressure, deep within the earth, can then transform any existing rock, igneous, sedimentary, or even other metamorphic rocks, into new metamorphic forms. And under even greater heat, they can melt back into magma, restarting the cycle. This is Earth's constant renewal, a tireless process of breakdown and rebirth. This ceaseless churning means that Earth's crust is never truly static. Rocks that formed billions of years ago, if they still exist, have likely undergone this cycle countless times, their original signatures blurred and rewritten by the immense forces at play. The oldest rocks we find are not necessarily the very first rocks formed, but rather the survivors, those that have managed to endure the ceaseless transformations. This cyclical nature is a testament to Earth's resilience, its ability to shed the old and embrace the new, to constantly remold its features. But to truly grasp the scale of this renewal, we must consider the immense energy that drives it, the primordial heat still simmering within our planet. And to understand that ancient heat, we must look back to the very formation of the Earth itself. The Earth's crust is not a single, unbroken shell. Instead, it is fractured into colossal pieces, like a cracked eggshell. These pieces are the tectonic plates, and they do not sit still. They float ever so slowly upon a sea of semi-molten rock beneath. This movement, this grand ballet of continents, is driven by a force so immense it reshapes landscapes over eons. Imagine the Earth's interior as a simmering cauldron, heat generated from radioactive decay, and the residual warmth of formation rises from the deep mantle. This heat creates slow-moving currents, much like water in a pot being heated from below. Where these currents rise, they weaken the overlying crust, creating vast upwelling zones. Conversely, where cooler material sinks, it pulls the crust downwards. These currents exert a relentless pull and push on the tectonic plates. Continents drift apart, new ocean floor is born, and mountains are thrust skyward. This constant rearrangement of Earth's surface is the very engine of geologic change, an invisible hand sculpting the planet's face. But the energy for this grand dance, this ceaseless shuffling of land masses, originates from a source even more profound. To truly comprehend the power behind plate tectonics, we must delve into the very moment our planet began to coalesce from the cosmic dust. The ocean floor, formed at the fiery seams of diverging plates, carries a heavy destiny. When this oceanic crust encounters the leading edge of a continental plate, a dramatic collision is inevitable. Gravity and the relentless pressure from the Earth's interior dictate the outcome. The denser, older oceanic crust, laden with the weight of thousands of miles of water, begins to bend and dive beneath the lighter continental mass. This is the essence of subduction. It is a process of relentless descent, a folding of the planet's skin into the fiery depths. As the oceanic plate plunges downward, it drags with its sediments and even fragments of other oceanic plates. It is a conveyor belt of destruction, recycling ancient crust back into the mantle's embrace. But this recycling is not without its spectacle. As the subducting slab grinds deeper, it encounters immense heat and pressure. Water trapped within its minerals is released, migrating upwards into the overlying mantle wedge. This influx of water lowers the melting point of the mantle rock, initiating a fiery transformation. Magma begins to form, a molten brew eager to ascend. And where this magma finds its path to the surface, the Earth's crust is dramatically altered. These rising pockets of molten rock can erupt, forming chains of volcanoes that often trace the very edge of the continental plate. These are the arcs of fire, the fiery scars left by the planet's ceaseless internal adjustments. Look closely at the edges of continents, and you will find these volcanic mountain ranges, a testament to the violent ballet of subduction. But what happens to the materials dragged down into the earth? and what deeper secrets lie within the fiery churn. To understand the ultimate fate of subducted material and the recycling of Earth's crust, we must examine the very process of igneous rock formation, the magma born from the Earth's deep heat, and the release of water within the subducting plate rises with an undeniable force. It collects in vast reservoirs beneath the surface, a volatile accumulation of molten rock and dissolved gases. When the pressure within these magma chambers becomes too great, the Earth can no longer contain it. This is when the volcano awakens. The eruption can be a gentle ooze of lava, a slow but steady flow that reshapes the landscape over time, or it can be a cataclysmic explosion. It is a release of pent-up energy, a shuddering breath from the planet's core. Ash plumes can climb miles into the atmosphere, carrying the dust of creation and destruction. Pyroclastic flows, superheated avalanches of gas and rock, can race down slopes with terrifying speed. But the spectacle of volcanoes is only one side of the coin. The same forces that drive magma towards the surface also create a different kind of tremor. As tectonic plates grind and shift against each other, particularly at their boundaries, stress builds. This built-up energy is stored within the rock, like a coiled spring. When that stress exceeds the strength of the rock, it is released in a sudden, violent rupture. This is an earthquake. The ground trembles, waves of seismic energy radiating outwards from the point of rupture, known as the hypocenter. The intensity of the shaking depends on the magnitude of the rupture and the distance from the epicenter. The point directly above the hypocenter on the Earth's surface, these seismic waves can propagate through the planet, offering us a fleeting glimpse into its unseen interior. Volcanoes and earthquakes, then, are not random events. They are the direct, dramatic consequences of tectonic plates in motion. They are the Earth's way of speaking, of readjusting, of shedding excess energy. But the patterns of these events are not uniform. Some regions are far more active than others. Why does this happen? The answer lies in understanding the specific characteristics of these tectonic boundaries and what happens when plates pull apart. To uncover this, we must explore the creation of new crust at divergent plate boundaries. The ground shudders, not from the violent eruption of magma, but from something subtler, a deep, internal unrest. As massive tectonic plates, the continents themselves, scrape and grind, they store immense pressure. It is a slow, persistent tension, accumulating over eons. Then, in a sudden, catastrophic release, this stored energy fractures the rock. This is the earthquake, a tremor that snakes its way through the crust. Seismic waves, invisible ripples of force, spread outwards, mapping the planet's hidden architecture. These forces, the building and the breaking of the Earth's shell, are not simple accidents. They are the Earth's deep breath, its constant work of self-rearrangement. But the places where this work is most intense, where the tremors are most frequent, and the fires most eager to erupt, are not random. They are dictated by the very nature of these boundaries. Some edges of the plates are places of collision, others of sliding past. But there is another, equally fundamental process to understand why certain zones are so volatile, why new land is born and old land is consumed. We must look to the places where the earth itself is pulling apart. It is here, at the divergent boundaries, that the slow, inexorable creation of new crust begins, a story written in molten rock and ocean trenches. And to see how this constant renewal shapes our planet, we must consider the air we breathe and how its very composition has shifted over unimaginable time. The air around us, so familiar, so essential, has not always been this way. Its composition traces a vast, ancient history, a testament to the silent, steady work of life itself. For billions of years, the early Earth's atmosphere was a far stranger, more toxic brew, devoid of the oxygen that sustains us today. It was a world dominated by gases like methane, ammonia, and carbon dioxide. A far cry from the clear skies we know. Life emerged in these harsh conditions. Simple, single-celled organisms that breathed something other than air. They processed the available chemicals, thriving in an environment that would be deadly to us. But then a revolution began. A new form of life, photosynthetic microbes, learned to harness the energy of sunlight. They captured carbon dioxide and, in a remarkable metabolic process, released a new gas as a byproduct. This gas was oxygen. Initially, this oxygen was a poison to much of the existing life. It reacted with other elements, forming new minerals and altering the very chemistry of the oceans. But slowly, relentlessly, the oxygen levels began to rise. It was a gradual transformation, a planetary alchemy powered by sunlight and microscopic life. This slow accumulation, this gradual oxygenation, is one of the most profound events in Earth's history. It set the stage for the evolution of all complex life, including our own. But to truly grasp the scale of this change, we must look back to the very first stages of this atmospheric evolution. The very air we breathe, the invisible blanket that shields our planet, is not a static entity. It is a dynamic, ever-shifting tapestry woven from countless chemical threads, each one carrying the imprint of deep time. For eons, the Earth's atmosphere has been a vast laboratory, its composition sculpted by geological forces and, remarkably, by the relentless activity of life itself. The story of our atmosphere is inextricably linked to the story of carbon, an element that has danced through geological eras, regulating our planet's temperature with a rhythm as old as the mountains. Carbon, in its many forms, has been a central character in Earth's unfolding drama. It dissolves in oceans, it forms the bedrock of continents, and it circulates through through the atmosphere, a constant exchange between the solid earth and the sky. This exchange, the grand cycle of carbon, is the planet's most fundamental thermostat. Think of it as the deep, slow breathing of the earth, a process that has kept our world habitable through unimaginable changes. When this carbon cycle falters, or when human hands accelerate its pace, the consequences are profound. We see the evidence in the slow creep of deserts, the rising of ancient seas. But to understand this delicate balance, we must first trace the carbon's journey through geological time, a path that reveals how life learned to sculpt its own environment, and how that environment, in turn, shaped life. We must understand the carbon cycle through time, regulating climate. The oceans themselves are not mere passive basins, but a vast circulatory system, a planetary engine of heat distribution. Imagine them as a colossal series of interconnected rivers, a liquid tapestry that spans the globe, carrying warmth from the tropics towards the frigid poles and returning cooler waters in a perpetual embrace. This constant movement, the oceanic currents, plays a role as crucial as the atmosphere in moderating our planet's climate. These currents are driven by a complex interplay of forces: the sun's radiant energy, the pull of the moon in its tidal dance, and the very rotation of the earth itself. They are the planet's arteries, plumbing that redistributes the sun's uneven blessings. Without them, the tropics would bake, and the poles would freeze into uninhabitable desolation. It is a system of immense power and delicate balance, a silent guardian of Earth's habitability. But the story of oceanic currents is not just one of physical movement. It is also a story of chemistry and life, of how dissolved minerals and gases are carried to the furthest reaches of the deep. And to truly grasp the intricate dance of heat across our planet, we must understand the forces that shape these vast, flowing rivers, and how they, in turn, shape life. We must explore the profound impact of oceanic currents, global heat distribution. The slow, steady pulse of oceanic currents carries more than just heat. They are conduits for a wealth of dissolved minerals, nutrients, and microscopic life. This constant exchange, this silent transport, is the very foundation upon which entire ecosystems are built. And in the warm, shallow waters of the Pacific, where sunlight penetrates and currents deposit their precious cargo, a miracle of geological proportion has unfolded over millennia. Here, in this sun-drenched cradle, lives an organism that builds structures visible from the void of space. These are not inert stones, but the accumulated exoskeletons of countless tiny creatures, each generation building upon the skeletal remains of the last. This living architecture, the Great Barrier Reef, is a testament to the persistent power of life and a remarkable geological archive. The coral polyps, architects of this underwater city, are minuscule animals that secrete calcium carbonate. Over vast stretches of time, these seafloor gardens grow, layer by layer, forming complex three-dimensional habitats. Each branching structure, each undulating mound, is a whisper from the past, a chronicle of changing sea levels, water temperatures, and the health of the surrounding ocean. Within this vibrant, pulsating metropolis, a staggering diversity of life finds refuge and sustenance. Fish of every hue dart through coral labyrinths, their movements a reflection of the currents that brought them here. Yet this living geology is far more fragile than the bedrock of continents. It is a delicate balance, exquisitely sensitive to the subtle shifts in its environment, a giant organism breathing with the rhythm of the tides. The reef's growth, its very formation, is a slow geological process, a patient mapping of ecological history. But what happens when the conditions that allowed it to flourish begin to change? Not over eons, but within human lifetimes. To understand this, we must delve into the unseen forces that shape and perhaps threaten this monumental living geological record, a record written in calcium carbonate and whispered by the ocean's breath. The calcium carbonate structures of the reef, brilliant and alive, hold a memory of sunshine, of light captured and transformed. But the earth holds other, deeper archives of stored sunlight, remnants of eras so distant they defy easy comprehension. These are the fossil fuels, the buried sunlight of ancient eras. Imagine a world bathed in a different light, a world teeming with life that pulsed with an energy now locked away in dense, dark layers beneath our feet. These are not mere rocks. They are the compressed, transformed bodies of countless organisms, creatures that once danced in sunlight long extinguished. The very energy we harness today, the power that drives our industries and lights our nights, is a profound echo of those ancient sunbeams. It is a captured moment from a forgotten epoch, a chemical memory of photosynthesis played out millions of years ago. This stored energy is a geological treasure, yes, but it is also a profound enigma. It speaks of cycles so vast, they make our own lives seem like fleeting moments. And as we draw this sunlight out, we stir a slumbering power that has been waiting for a very, very long time. But the story of this stored sunlight is not just one of energy. It is a story of immense geological pressure, of time measured in epochs, and of a fragile balance that has been undisturbed for millennia. What happens when we awaken this ancient power? And what are its true origins? Written not in coral, but in the very fabric of the earth's oldest stones. To understand this, we must journey into the deep past, to the very origins of the planet's buried light. The layers of rock beneath us are not just inert stone. They are a vast library, each stratum a page turned in Earth's chronicle, and within them lie the silent testaments of lives long past, the fossils. These are not the dramatic remnants of roaring beasts alone, though those are certainly present. They are the delicate impressions of leaves, the intricate skeletons of microscopic organisms, the hardened footprints of creatures that walked when the continents were in different places. Each fossil is a whisper from another time, a frozen moment of existence. They speak of extinct ecosystems, of alien landscapes, and of evolutionary pathways that have since diverged or ended. When we look at a fossil, we are seeing sunlight captured by life, then preserved through immense geological time and pressure. The sheer variety of fossil forms is staggering, from the ancient trilobites that scuttled across Cambrian seabeds to the colossal dinosaurs that once roamed vast plains. Each find offers a unique perspective, but the deeper we dig, the stranger the stories become, hinting at life forms that challenge our modern understanding of biology. These ancient remains are not just curiosities, they are vital clues, piecing together the grand narrative of life's unfolding on our planet. They show us the slow, relentless march of evolution, the rise and fall of species, and the profound interconnectedness of all living things across the vast canvas of deep time. The process of fossilization itself is a remarkable, rare event. It requires specific conditions, rapid burial, a lack of oxygen to prevent decay, and immense pressure over eons to transform organic matter into stone. This rarity makes each discovered fossil an even more precious window. But what if the fossil record itself is incomplete, a fragmented narrative that hints at entire chapters we can only guess at? What hidden dramas unfolded in the silent eras before our own? And what do these buried remnants truly tell us about the nature of life itself and its enduring will to persist? To peer into these deeper mysteries, we must consider the very origins of cells and the earliest forms of life. The fossil record, a tapestry woven from eons, reveals a startling truth. Life on Earth has not progressed in a steady, unbroken line. Instead, it has been punctuated by catastrophic events, moments when the vibrant pulse of biodiversity suddenly falters, leaving behind a ghostly silence. These are the mass extinctions. We often think of evolution as a slow, predictable climb, a gradual adaptation that weeds out the weak. But the history written in stone suggests a more violent, unpredictable path. Entire phyla, once flourishing, vanish without a trace. What force could so effectively scour the living world? These great die-offs are not mere footnotes. They are seismic shifts that redefine the biosphere, clearing the stage for new forms to emerge. It is as if Earth itself periodically sheds its skin, a painful but necessary renewal. But are these events random acts of cosmic violence, or are they inherent to the rhythm of a living planet? The sheer scale of loss during these periods is difficult to comprehend. Imagine millions of species disappearing within the blink of a geological eye. Yet, even in the face of such devastation, life finds a way. Resilience, adaptation, and sheer chance collide. These extinctions challenge our very understanding of natural selection. If species are constantly adapting to survive, how can so many be so utterly wiped out? It suggests forces at play far grander and more destructive than the daily struggle for existence. We see the layers of rock, and within them, the stark lines of absence. The question arises, are these events governed by predictable cycles, like the tides of an ancient ocean, or are they chaotic disruptions, random blows from an indifferent cosmos? The evidence points towards a complex interplay of both, a cosmic dance of creation and destruction. To understand the why, we must look at the forces that shape our planet and its orbit, a journey that takes us to the very edge of our solar system. The vastness of the cosmos holds more than just distant suns and nebulae. It harbors potential agents of profound change, objects that traverse the dark expanse with unfathomable power. Among these are asteroids, remnants of creation's earliest moments, hurtling through space on orbits dictated by gravity's subtle hand. These celestial wanderers, some mere pebbles and others colossal mountains, are not passive observers of cosmic evolution. They are active participants, their paths occasionally intersecting with the delicate dance of our own planet. When such a collision occurs, the consequences are not localized. They ripple across the globe, reshaping continents and rewriting the very script of life. Consider the sheer kinetic energy unleashed. A body of sufficient size impacting Earth would vaporize rock, eject molten material into the atmosphere, and trigger seismic waves that would girdle the planet. It is a force that could instantly erase entire ecosystems, plunging the world into a prolonged period of darkness and ecological chaos. Some scientists have begun to piece together the evidence, noticing strange patterns in the geological record. But are all impacts of this magnitude? Or are there subtler, yet still significant, interactions with these cosmic visitors? The layers of rock beneath our feet may hold the keys, revealing a history written not just by geological forces, but by celestial ones. To understand our planet's past, we must first consider the role of asteroids and cosmic impacts on Earth. The very star that gives our world its warmth, the sun, is not a static, unwavering source of light. It breathes, inhales, and exhales in cycles that stretch from mere years to eons. These solar rhythms, subtle shifts in its output, have long been suspected of influencing our planet's delicate climate. Imagine the sun's electromagnetic breath, its flares and sunspots waxing and waning. These changes, though seemingly small, send ripples outwards. They can subtly alter the amount of energy reaching Earth, nudging global temperatures. You may have noticed how certain periods of history seem to align with cooler or warmer spells. A coincidence, perhaps, but one that points to a deeper connection. These external forces, originating light years away, can act as unseen hands on Earth's thermostat. They are a constant reminder that our planet's story is not solely written by its internal geological processes. Something else is at play, a grander cosmic orchestration. But how precisely do these solar cycles translate into terrestrial weather? And what about the longer, more enigmatic solar patterns? To truly grasp Earth's climate, we must look beyond the planet itself and examine the powerful, periodic influences of the sun beneath the skin of the Earth. Far from the sunlit surface, a different kind of process unfolds. It is a slow, immense churning, a secret heart beating with molten rock. This is the realm of the deep Earth, where forces unseen shape the very ground we stand upon. Here, the mantle, a vast ocean of viscous rock, flows with unimaginable patience. Heat from the core, a furnace billions of years old, drives this sluggish circulation. Like a cosmic convection oven, it carries continents on its back, pulling them together and tearing them apart over vast stretches of time. These currents, hidden beneath miles of solid stone, are the true architects of our planet's surface. They are responsible for the great mountain ranges that scrape the sky and the abyssal trenches that plunge into darkness. The subtle shifts in this deep flow can trigger earthquakes and volcanoes, sudden outbursts of the planet's inner rage. You may feel the tremor of an earthquake, a violent shudder that shakes your world. But this is merely the surface echo of the monumental ballet happening far below. The forces at play are so immense, so ancient, that they dwarf our brief existence. But what lies at the very heart of this subterranean furnace? What secrets does the Earth's core hold? And how does its immense heat sustain these deep Earth processes that sculpt our planet's face? To understand the forces that shape our world, we must venture even deeper into the core itself, far beneath the flowing mantle. A realm of unimaginable pressure and temperature awaits. This is the Earth's core, a place where matter itself behaves in ways that challenge our everyday experience. It is not a solid, inert ball, as one might imagine. Instead, it is divided into two distinct parts. The outer core is a churning sea of molten iron and nickel, a metallic ocean in constant, turbulent motion. This fluid dynamism is the key. It is within this vast, superheated liquid that the Earth's most vital shield is born. The intense heat, a remnant of planetary formation and radioactive decay, generates powerful convection currents. These currents, like immense rivers of metal, flow and eddy. As this electrically conductive fluid moves, it creates and sustains an electric current. And where there is flowing electric current, there is a magnetic field. Think of it as a planetary dynamo, a vast, self-sustaining generator hidden at our planet's heart. But the story of this dynamo is not one of perfect, unwavering constancy. The flow within the outer core is chaotic, unpredictable. It shifts and writhes, and with it, so does the magnetic field it generates. This field, our invisible guardian, is not static. It waxes and wanes, its strength fluctuating over geological timescales. Most remarkably, the magnetic poles themselves are not fixed points. They drift, wander, and at times have even completely reversed their polarity. Imagine the North Magnetic Pole slowly migrating across the globe, a subtle dance guided by the churning metal miles below. This magnetic field, generated by the Earth's fiery core, is a silent, ever-present force. It deflects the constant barrage of charged particles from the sun, the solar wind. Without this magnetic shield, our atmosphere would be stripped away, rendering the surface a harsh, barren landscape, incapable of supporting life as we know it. It is a delicate balance, maintained by the inferno at our planet's center. But what happens when this dynamo falters? When the magnetic field weakens or shifts dramatically? What are the consequences for the life that has evolved under its protective embrace? To truly grasp the fragility of our existence, we must consider the profound implications of a changing magnetic shield. The churn within the outer core sends ripples upward, influencing the layers above. Deeper still, beneath the crust we inhabit, lies a vast, semi-molten ocean of rock, the mantle. This immense region, making up the bulk of our planet, is not passive. It is alive with slow, colossal currents, a sluggish, ceaseless convection cycle that acts as the true engine of Earth's dynamic surface. Heat from the planet's deep interior, a legacy of its fiery formation and radioactive decay, drives this convection. Hotter, less dense material wells up from the depths, while cooler, denser material sinks back down. It is a slow ballet of rock, a grand geological breathing that takes millions of years to complete a single cycle. You can almost feel the immense power, the raw, planetary forces at play. These vast, swirling currents within the mantle drag and shear the rigid tectonic plates that float upon its surface. Think of them as immense rafts. These plates, carrying continents and oceans alike, where the mantle currents push up, new crust is formed. Where they pull apart or slide past each other, great geological dramas unfold. It is this mantle convection that dictates the very shape of our world. It is responsible for the slow drift of continents, the building of mountain ranges, the opening of ocean basins, and the deep, silent trenches that scar the ocean floor. This invisible, ponderous movement has sculpted every landscape you have ever seen, every continent, every island. But the immense forces at play within the mantle are not always uniform. There are regions of intense upwelling, known as plumes, that can punch through the lithosphere, creating volcanic hotspots like Hawaii. And there are zones of slow, inexorable sinking, where old oceanic crust is drawn back into the abyss. It is a constant process of renewal and destruction, a planetary metabolism, and to fully understand how this immense convective engine shapes our world, we must now turn our attention to the boundary where these colossal plates interact. For it is here that the true violence and wonder of our planet are most dramatically revealed. The surface of the early Earth was a stark, alien place. It was a world still cooling from its fiery birth, bombarded by debris from the nascent solar system. The question of water, the very substance that defines our planet, hangs like a mist over this primordial era. Was it a gift from the heavens, delivered by icy visitors? Or was it already present, an intrinsic part of Earth's formation? The prevailing theories often point to comets and asteroids, those celestial wanderers rich in frozen volatiles. Imagine vast, icy bodies, remnants of the solar system's formation, impacting a young, parched Earth. These impacts would have released enormous quantities of water vapor, slowly accumulating over eons, perhaps seeding the planet with the oceans we know today. The isotopic signatures of water found in some meteorites offer tantalizing hints that this celestial delivery system might indeed be responsible. But another compelling idea suggests water was an inherent component from Earth's very beginning. As the planet accreted from the primordial dust and gas, volatile elements, including water molecules, could have been incorporated into the very rocks that formed our world. Deep within the Earth's mantle, scientists have found evidence of water trapped within minerals, suggesting that our planet might have been born with a significant internal reservoir. To truly grasp the origin of our oceans, we must consider the violent cataclysm that may have played a pivotal role in shaping the early Earth. The Earth's steadfast companion, the Moon, has not always graced our skies in its current form or at its present distance. Its very presence has orchestrated a profound dance with our planet, a celestial waltz that has shaped coastlines and dictated the rhythm of life for billions of years. When our planet began to take shape, the Moon was much closer, a colossal presence hanging low in the young sky. This proximity meant that the gravitational pull between Earth and Moon was far more intense. Imagine tides that were not gentle whispers, but powerful surges, colossal waves that would have swept far inland, reshaping continents with relentless force. This powerful tidal locking created a friction, a slow grinding that has had a surprising effect over cosmic timescales. This ceaseless tug of war between Earth and Moon has a subtle but significant consequence. The Moon is slowly drifting away. Each tidal cycle, the Earth's spin transfers a tiny amount of energy to the Moon, an almost imperceptible push that nudges our lunar neighbor further into the void. This phenomenon, known as tidal recession, means that the Moon we see today is not the Moon that hung in Earth's ancient skies. The implications of this celestial migration are staggering. Our planet's rotation has also been gradually slowing, a consequence of the same energy exchange that pushes the moon away. The days we experience are longer now than they were in Earth's infancy, a testament to the long, slow work of lunar gravitational influence. And as the moon recedes, the intensity of Earth's tides diminishes, altering the very forces that have sculpted our planet's surface, and perhaps even guided the earliest forms of life. This gradual separation, this cosmic distancing, begs a question about the early Earth's environment. If the tides were so much more powerful in the past, how did this violent churning affect the very beginnings of life as we understand it? To explore this, we must delve into the planet's earliest restless days, a time before even the first tentative stirrings of life could be imagined. The face of the moon, scarred and ancient, tells a story etched in impact. Every crater, from the grandest basin to the smallest pockmark, is a silent testament to a violent past, a cosmic history written in stone. These are not mere blemishes. They are windows into a time when the solar system was a far more chaotic place, a busy cosmic thoroughfare. Each impact crater is a record of a collision, a moment of intense energy released as a celestial body met the lunar surface. The size and distribution of these craters offer a unique timeline, a natural clock ticking backward through eons. Larger craters often reveal deeper, older impacts, while fields of smaller ones indicate more recent, or perhaps more numerous, smaller impacts. But the more we study these scars, the more we realize they are more than just evidence of past chaos. They are a chronicle of the bombardment that shaped not just the moon, but our own Earth too. The moon, lacking an atmosphere and active geology, preserves these records with an unparalleled fidelity, acting as a silent, unblinking witness to the early days of our planetary neighborhood. The sheer number of craters suggests an early solar system awash with debris. Objects that might have once struck Earth have left their indelible marks on its unchanging companion. What does this constant rain of cosmic debris tell us about the very conditions under which our planet formed and began its slow journey towards habitability? To understand this, we need to peel back one more layer of time and look at the moon's stark, cratered surface. The moon's craters, then, are not just holes in the ground. They are a library of impacts, each one a chapter in the story of our solar system's formation and evolution. By studying their shapes, their depths, and their distribution, we can begin to reconstruct the intensity of the early bombardment, a process that profoundly influenced the nascent Earth. But what if these impacts were not just random acts of destruction, but held a deeper, more interconnected significance to the very building blocks of worlds? This question leads us to consider the moon's impact basins and the material they have ejected. We gaze at the moon, a scarred and ancient face, and wonder about the universe beyond. The craters, those silent mouths etched into its surface, speak of a time when our solar system was a more violent place. Each impact basin is a record, a testament to the cosmic dust and rock that once swept through the void unchecked. It's a powerful reminder of the forces that governed the early days of our planet, and by extension, the potential for life elsewhere. This ancient record on the moon, though stark and desolate, offers a unique perspective. It shows us a universe far from empty, teeming with matter in its rawest form. We see the remnants of collisions that sculpted worlds, and it's here, in the face of this cosmic violence, that a profound question begins to form. If our Earth was shaped by such events, and if the universe is so vast and filled with so many potential worlds, then where do we fit into this grand celestial tapestry? The sheer scale of the cosmos, the endless dance of stars and galaxies, can feel overwhelming. Yet within this immensity, there lies a stirring possibility. The same chemical elements that form our bodies, our planet, and our sun are scattered across the universe. This cosmic inheritance fuels a persistent hope, a quiet whisper that perhaps, just perhaps, we are not alone in this vast expanse. It's a thought that draws us outward, beyond the familiar glow of our sun, to ponder the existence of other worlds, other possibilities, and the enduring quest to find extraterrestrial life, and to truly grasp our potential place in this cosmic drama. We must first understand the vastness of the stage upon which it all unfolds. The celestial sphere above us is a tapestry woven with light from countless stars, each one a sun potentially orbited by its own family of worlds. We have peered into the depths of space with instruments that pierce the veil of distance, revealing a universe far more populated with planets than we once dared to imagine. Scientists now estimate that there are more planets than stars in our own galaxy, and our galaxy itself is but one among billions. Consider the sheer numbers. Billions of galaxies, each containing billions of stars, each with a high probability of hosting planetary systems. If life arose on Earth under conditions that seem, in retrospect, not entirely unique, then it stands to reason that life should have arisen on countless other worlds. Some of these worlds, given the age of the universe, would have had billions of years to develop intelligent civilizations, perhaps far exceeding our own in technological prowess and cosmic reach. Yet, when we turn our instruments towards the heavens, searching for any sign of these hypothetical civilizations, we find only silence. This profound quiet is the heart of what is known as the Fermi paradox. It asks a simple, yet deeply unsettling question. If the universe teems with possibilities for life, and if intelligent life has had ample time to develop and spread, then where is everybody? This silence in the cosmic ocean is not merely an absence of evidence, but a powerful presence of absence, urging us to look closer at our assumptions. It is easy to feel the weight of this question when gazing at the night sky. Each distant point of light represents a universe of possibilities, a grand experiment in planetary formation and the potential for life. We send out our radio signals, our probes, our eager questions into the void. And for now, the void answers with its own vast emptiness. This paradox challenges our understanding of life itself and our place within the grand cosmic narrative. It forces us to confront the possibility that something fundamental might be missing from our equations, some missing piece of the puzzle that explains why the universe, for all its potential, appears so solitary. But what if the silence itself is a clue? What if the very nature of cosmic evolution, or the inherent challenges of interstellar communication, create a barrier that has thus far remained insurmountable? The absence of any verifiable contact or observation of extraterrestrial intelligence necessitates a deeper inquiry. It compels us to consider explanations that range from the mundane to the profoundly existential. Perhaps life is far rarer than we assume, or perhaps intelligent civilizations simply do not last long enough to make their presence known across the vast distances of space. The Fermi paradox, then, is not just a scientific puzzle. It is a philosophical one. It probes the very foundations of our understanding of life, intelligence, and the universe. Why has no alien signal reached us? Why have no alien artifacts been discovered? The question echoes across the cosmic gulf, a persistent whisper in the face of overwhelming statistical probability. To begin to unravel this enigma, we must consider the many possible resolutions, and one of the most immediate is to examine the sheer scale and complexity of the universe itself, and how that complexity might be governed by unseen forces. The universe is a place of immense scale and unimaginable age. Stars are born and die, galaxies collide, and planets form and erode over eons that dwarf human comprehension. Within this grand cosmic theater, the emergence of life, let alone intelligent life capable of interstellar communication, might be an exceedingly rare event. Or perhaps the stages of development for intelligent species are so diverse and varied that our current methods of detection are simply inadequate for finding them. The sheer diversity of potential life forms and evolutionary pathways across the cosmos presents a daunting challenge to our search. And in considering these possibilities, we must also acknowledge the immense distances involved. The nearest star system to our own, Alpha Centauri, is over 4 light-years away. Even if an advanced civilization existed there, the signals they send would take years to reach us, and any response would take equally long. The sheer energy and technological investment required for sustained interstellar communication or travel are staggering. This vastness of space, this cosmic ocean, is not an easy medium for an exchange of information or for interspecies visitation. This challenge of distance, coupled with the potential rarity of life, leads us to consider a variety of potential explanations for the cosmic silence. Some theories propose that intelligent civilizations are inherently self-destructive, extinguishing themselves before they can achieve widespread interstellar presence. Others suggest that the universe may be a zoo, where advanced civilizations intentionally avoid contact with less developed ones like our own, observing us from afar without intervention. These are not comforting thoughts, but they are logical extensions of the paradox. The implications of the Fermi paradox are profound. They suggest that either life, or intelligent life, or technologically advanced civilizations are far rarer than we expect, or there are significant barriers to their detection or expansion. Each proposed solution to the paradox opens up new avenues of thought and research, forcing us to reevaluate our place in the cosmos and the potential trajectory of our own civilization. It is a profound moment of introspection, prompted by the silence of the stars. And as we contemplate these vast cosmic silences, we must also consider the possibility that our very understanding of intelligence and civilization might be too narrow, too anthropocentric. What forms could intelligence take on worlds vastly different from our own? What would motivate a civilization that had mastered interstellar travel and communication? These are the questions that beckon us forward, driving our curiosity towards understanding the deeper mechanisms that might govern the emergence and persistence of life in the universe. This leads us to explore the profound concept of the great filter. The universe we perceive, the one filled with stars, galaxies, and nebulae, is but a fraction of what truly exists. Its visible substance, the matter we can observe through telescopes and detect with our instruments, accounts for a mere 5% of the cosmos. The remaining 95% remains shrouded in mystery, composed of two enigmatic entities known as dark matter and dark energy. These unseen components are not mere theoretical constructs. Their existence is inferred from their profound gravitational effects on visible matter and the expansion of the universe itself. Dark matter, for instance, acts as an invisible scaffolding, its gravity holding galaxies together, preventing them from spinning apart. Without it, the celestial structures we admire would simply dissipate into the cosmic void. The way galaxies rotate, faster than the visible matter alone could explain, is a primary piece of evidence for dark matter. It's like seeing a carousel spinning at a speed that suggests far more weight than its visible horses could provide. But this invisible mass is not ordinary matter. It doesn't emit, absorb, or reflect light, rendering it invisible to all our current forms of detection. A ghost in the cosmic machine. Dark energy, on the other hand, is even more perplexing. It is the force driving the accelerated expansion of the universe. For decades, astronomers assumed that gravity would be slowing down the cosmic expansion. Instead, observations revealed the opposite. Space itself is stretching, and the rate at which it is stretching is increasing. This implies a repulsive force at play, an energy inherent in the fabric of space-time, pushing everything further apart. Imagine a loaf of raisin bread rising in an oven. The raisins represent galaxies, and the dough represents space. As the dough expands, all raisins move away from each other. But imagine if, as the bread rises, the raisins started moving apart even faster, as if some invisible force was actively pushing them. That force, that unexplained acceleration, is what we attribute to dark energy. It's a cosmic push, a relentless expansion that shapes the ultimate fate of the universe. The precise nature of both dark matter and dark energy remains one of the greatest unsolved mysteries in science. Are they new particles, new forces, or do they hint at a fundamental flaw in our understanding of gravity and the cosmos? To truly grasp the universe's story, we must delve deeper into the unseen architects of its structure and its destiny, and to understand how these unseen forces came to dominate the cosmos. We must return to the very beginning, to the fleeting moments after the Big Bang and the subsequent rapid inflation of the universe. The universe, as we perceive it, is a vast and intricate tapestry. But what if this tapestry is merely one thread in an infinite weave? The concept of a multiverse, a collection of countless universes, each potentially with its own unique laws of physics and constants, has moved from the realm of science fiction to serious scientific inquiry. It is a mind-bending idea, suggesting that our reality might be just one bubble in an ocean of existence. Consider the possibility that the extreme conditions and rapid expansion immediately following the Big Bang, a period known as cosmic inflation, could have spawned not just our universe, but an endless number of others. Each inflationary event, a brief surge of exponential expansion, could have pinched off and sealed away its own pocket of space-time, creating an entirely separate universe. Imagine these universes as bubbles forming in boiling water, each one distinct and independent. Within this grand cosmic architecture, our universes seemingly fine-tuned, constants the precise values of fundamental forces and particle masses that allow for stars, galaxies, and life to form might not be a miracle, but a statistical inevitability. If there are an infinite number of universes, then surely there must be at least one out of an unimaginably large set, where these constants just happen to be exactly right for observers like us to exist. It's a way of explaining our existence without resorting to a deliberate design. But how can we ever hope to test such a radical idea? Direct observation of other universes is by definition, impossible if they are truly separate and causally disconnected from our own. Yet, some theoretical physicists propose that subtle signatures, faint echoes of these other realities, might have imprinted themselves on our own universe during its earliest moments. These could be detectable as unusual patterns in the cosmic microwave background radiation, the afterglow of the Big Bang. The implications are profound. If the multiverse is real, then our quest to understand the laws of physics might be incomplete. We would need to consider not just the rules of our universe, but the rules that govern the entire ensemble of universes. It forces us to confront the possibility that what we observe so carefully might be unique only to our particular cosmic bubble and not a universal truth, and to truly explore the boundaries of what is knowable. We must now turn our gaze even further inward towards the fundamental nature of reality itself and the strange quantum realm that underpins it all. The universe, however grand and vast, is not an eternal engine. Even amidst the cosmic ballet of creation and destruction, a different kind of end looms, a slow fade rather than a cataclysm. It's a concept known as the heat death of the universe. Imagine a universe where all the energy has spread out as thinly as possible, where no temperature differences remain to drive any processes. In this far future, stars will have long since burned out, their final embers extinguished. Black holes, the cosmic behemoths, will have slowly evaporated through Hawking radiation, leaving behind only the faintest whispers of their existence. Galaxies will have drifted apart, their constituent stars scattered among the cold, dark voids. It's a state of ultimate equilibrium, a perfect, silent stillness. This state isn't a sudden event, but an unimaginably slow process, unfolding over timescales that dwarf even the age of the universe we know. It's a universe that has reached its maximum entropy, a state where disorder reigns supreme, and no further work can be done. Every particle, every energy wave has settled into its lowest possible configuration. But within this seemingly final quietude, a question lingers. Could there be structures, or perhaps even forms of existence, that defy this thermodynamic equilibrium? To understand how such a state might be reached and what it truly signifies for the nature of reality, we must delve into the fundamental laws that govern the universe's ultimate fate. And to fully grasp this potential end, we must first understand the very fabric of space and time and the enigmatic forces that shape them. The cosmic web, a vast tapestry of galaxies and dark matter, is not as uniform as it once appeared. Our Milky Way, once thought to be drifting serenely in a relatively empty expanse, is being pulled by an unseen, immense gravitational force. This anomaly, this cosmic anomaly, is known as the Great Attractor. It sits roughly 250 million light years away, a region of space so densely packed with galaxies that its gravity overwhelms the expansion of the universe in our local neighborhood. Imagine a colossal eddy in the cosmic ocean, drawing everything towards its center. Our galaxy, along with hundreds of thousands of others, is caught in this current, hurtling towards an unknown destination. This gravitational behemoth is not a single object, but rather a vast supercluster, a concentration of mass that warps spacetime around it. The light from some of the galaxies within the Great Attractor is so distorted and redshifted that it's difficult to observe directly. Yet its presence is undeniable, a silent, insistent tug on everything we can see. The very existence of the Great Attractor challenges our understanding of the universe's large-scale structure. It suggests that the cosmic web may be far more complex and dynamic than our initial models predicted. It's a reminder that even in the grandest scales, there are mysteries that lie just beyond our current sight. But what exactly resides at the heart of this immense gravitational well? And what does its influence truly mean for the future of our galactic home? To find out, we must navigate a region of space obscured by dust and gas, a place where the universe's deepest secrets may be hidden. And to do that, we must first understand the structures that lie between us and this cosmic enigma. The shimmering veil of the observable universe is not a solid boundary, but a horizon, a limit defined by the speed of light and the age of the cosmos. Imagine standing on a vast, dark plain, the stars above us like scattered diamonds. We can see them, their light traveling across unimaginable distances to reach our eyes. But there is a point, a distance beyond which their light simply has not had enough time to reach us since the universe began. This is the edge of what we can perceive, the boundary of our cosmic vision. This horizon is not static. As time marches forward, light from ever more distant objects has the chance to arrive, slowly expanding the sphere of what we can see. Yet the universe itself is expanding, a relentless stretching of space that pushes these distant frontiers further away, even as we strain to observe them. Some regions, though they may be visible to us today, are already receding faster than light, forever lost to our direct gaze, lost to the cosmic tide. The light that reaches us from the farthest reaches of the observable universe is ancient, a whisper from the universe's infancy. It carries the imprints of a time before stars, before galaxies, when the cosmos was a hot, dense fog of plasma. Studying this faint relic radiation, this cosmic microwave background, is like deciphering the earliest echoes of creation itself. It reveals the universe's initial conditions, the seeds from which all subsequent structure would grow. But even within this ancient light, there are subtle hints of something more, anomalies that suggest the grand cosmic tapestry may be woven with threads we are only beginning to perceive. As we push the limits of our instruments, we begin to question what lies just beyond this radiant edge, what cosmic structures might exist that forever escape our sight. To truly understand the universe, we must contemplate not only what we can see, but also the profound implications of what remains forever hidden from us. And to grapple with this ultimate unknowable, we must consider the very fabric of reality and the fundamental forces that shape it. The silence that surrounds us, a profound stillness, is not truly empty. It hums with a faint, pervasive warmth, a whisper from an age so distant it predates the very concept of light as we know it. This is the cosmic microwave background, the afterglow of creation itself, a faint radiation bathing the entire cosmos. It is an echo frozen in time, a snapshot of the universe when it was a mere infant, a mere 380,000 years old. Before this moment, matter and energy were so tightly bound in a searing, opaque plasma that light could not travel freely. But as the universe expanded and cooled, protons and electrons finally found each other, forming neutral atoms. This cosmic dawn, this decoupling, allowed photons to stream outwards for the first time, carrying the story of that primordial state. Observing this ancient light is like peering through a veil into the universe's earliest memories. It reveals the initial, almost perfect uniformity of the cosmos, but etched within it are subtle temperature fluctuations. These tiny variations, these ripples in the primordial soup, are the seeds from which all the grand structures we see today, galaxies, clusters, and the vast cosmic web, would eventually grow. It's a breathtaking testament to order emerging from apparent chaos. But even in this seemingly uniform echo, there are whispers of mystery. We see patterns, anisotropies, that are perhaps not quite as random as they first appear. There are hints of a cosmic architecture that might challenge our current understanding. To truly grasp the import of these cosmic whispers, we must delve into the fundamental forces that governed this early universe and how they sculpted the reality we inhabit. The enduring power of the cosmic microwave background lies in its direct link to the very genesis of everything. It's a constant reminder that the universe was not always this vast, structured expanse. It began as something far more elemental, and understanding its earliest moments is key to understanding its ultimate fate. To truly comprehend the forces that shaped this ancient light, we must now turn our attention to the unseen architects of the cosmos, the fundamental forces themselves. The light we detect, the faint afterglow of creation, is a tapestry woven by fundamental interactions. It speaks of a time when the universe was a dense, energetic broth, and two of the most dominant forces, gravity and electromagnetism, were already beginning their grand, eternal dance. These are not mere abstract concepts. They are the unseen sculptors of reality, the silent partners in every cosmic drama. Gravity, the force that pulls us to the Earth, that holds stars in galaxies and galaxies in clusters, was already at play in those nascent moments. It was the gentle, persistent tug that began to gather the slightly denser regions of the early universe, setting the stage for the formation of the very first structures, even the subtlest variations in that primordial energy map. The cosmic microwave background were whispers amplified by gravity's ever-growing influence. But gravity was not alone. Electromagnetism, the force behind light itself, behind the chemical bonds that form atoms and molecules, was also a critical player. It governed the interactions of charged particles, dictating how matter and energy would behave in that intensely hot, dense early state. The very light carrying the story of creation is a product of electromagnetic forces at work. These two forces, though vastly different in their expression, are inextricably linked in the cosmic narrative. One pulls together, the other binds and repels, and their interplay shaped the initial distribution of matter and energy. It's a subtle but profound revelation. We see the grand structures of the universe only because of this delicate balance, this cosmic choreography. And to understand how this delicate balance led to the universe we know, we must now consider the other fundamental forces that joined this cosmic composition. The universe, it seems, is remarkably hospitable, not just to stars and galaxies, but to life. This isn't an accident of chance. It's a delicate, almost improbable arrangement of fundamental constants, the very numbers that define how physics works. When we look at these values, they appear exquisitely tuned. Consider the strength of the electromagnetic force, or the mass of subatomic particles. If these numbers were even minutely different, the universe, as we know it, could not exist. Stars might not ignite. Atoms might not form stable bonds, and the complex chemistry necessary for life would be impossible. It's as if the universe was set with a precision dial, each setting critical for the next. This fine-tuning suggests a profound question. Are these constants simply a lucky draw from a cosmic lottery? Or is there something more at play? The sheer improbability of these values, aligning so perfectly to permit existence, is staggering. It whispers of an underlying order, a deliberate scaffolding upon which reality is built. The forces we've discussed, gravity and electromagnetism, are governed by these constants. Their interactions, their very ability to shape the cosmos, depend on these precise numerical values. And to truly grasp the implications of this cosmic precision, we must delve into the other two fundamental forces that govern the universe. The universe, it seems, is remarkably hospitable, not just to stars and galaxies, but to life. This isn't an accident of chance. It's a delicate, almost improbable arrangement of fundamental constants, the very numbers that define how physics works. When we look at these values, they appear exquisitely tuned. Consider the strength of the electromagnetic force or the mass of subatomic particles. If these numbers were even minutely different, the universe, as we know it, could not exist. Stars might not ignite, atoms might not form stable bonds, and the complex chemistry necessary for life would be impossible. It's as if the universe was set with a precision dial, each setting critical for the next. This fine-tuning suggests a profound question. Are these constants simply a lucky draw from a cosmic lottery? Or is there something more at play? The sheer improbability of these values, aligning so perfectly to permit existence, is staggering. It whispers of an underlying order, a deliberate scaffolding upon which reality is built. The forces we've discussed, gravity and electromagnetism, are governed by these constants. Their interactions, their very ability to shape the cosmos, depend on these precise numerical values. And to truly grasp the implications of this cosmic precision, we must delve into the other two fundamental forces that govern the universe: the nature of time, a flow or an illusion. We experience existence as a river, a relentless current carrying us from past to future. This sense of unfolding, of moments arriving and then vanishing forever, is deeply ingrained. But what if this familiar flow is not the fundamental truth of reality, but rather a perception, a trick of consciousness? What if time, as we understand it, is an illusion woven into the fabric of our minds? Physics, particularly at its most fundamental levels, often struggles to grant time this privileged unidirectional status. In the equations that describe the universe, time frequently appears as just another dimension, no different from space. There's no inherent arrow, no built-in tendency to move forward. This suggests that the pervasive feeling of a flowing present might be an emergent property, something our brains construct to make sense of a more complex, timeless reality. It's a deeply unsettling thought, one that challenges our very perception of being. We see the universe's most ancient light, yet we cannot glimpse its future. This one-way passage feels absolute, but the deeper we peer into the quantum realm, or ponder the vast indifference of cosmic scales, the more this linear experience begins to fray. The universe's clockwork, when stripped bare, may not tick in the way we instinctively feel it does. This brings us to a profound consideration. If time is not the simple, linear progression we experience, what then underpins our perception of change and duration? To understand this, we must consider the very essence of what constitutes reality and how our perception of it is shaped by forces we are only beginning to comprehend. The nature of time itself, whether a river or a stagnant pool, is a question that pulls us toward the limits of our understanding. And to reconcile our experience with the universe's silent language, we must explore the very architecture of existence, moving beyond our immediate senses to grasp the deeper currents. we stand at the edge of comprehension, gazing into the unfathomable abyss of existence. The universe, in its silent, indifferent majesty, offers no easy answers. Our lives, fleeting sparks against an backdrop of unimaginable epics, are but a blink in the grand, cosmic narrative. Yet, within this brief illumination, we possess the unique capacity to ponder the very nature of being, to question the fabric of reality that enfolds us, consider the immense stretches of time, the eons that preceded our arrival and will surely outlast our departure. This perspective, the contemplation of deep time, is a mirror reflecting our own transient place. It is a powerful, almost melancholic exercise to feel the weight of ages pressing down, to understand that mountains rise and fall, oceans boil and freeze, and entire species bloom and vanish, all within the silent hum of the cosmos. But within this vastness, there is a peculiar resonance. The patterns we observe, the cycles of birth and decay, the rhythmic ebb and flow of celestial bodies, whisper of underlying principles. These are not mere random occurrences, but echoes of fundamental forces, etched into the very essence of space and time. We are drawn to these echoes, compelled by an insatiable curiosity to decipher the silent language of the universe. It is a language written not in words, but in the immutable laws that govern stellar evolution, the formation of galaxies, and the delicate dance of subatomic particles. The deeper we look, the more we realize that our own existence, and indeed all existence, is woven from the same cosmic threads. The true mystery, however, lies not just in the grand cosmic sweep, but in the quiet persistence of consciousness itself. Why are we here to witness this? Why do we possess this yearning to understand? The universe offers its grand spectacle, but the meaning we derive from it, the awareness that blossoms within us, that remains an enduring enigma. What if our perception of time, this fundamental aspect of our reality, is merely a tool, a mechanism evolved to navigate a universe far stranger than we can fully grasp? To unravel this, we must confront the very limits of our understanding and explore the profound implications of a reality unbound by our linear experience. Make sure to subscribe for more videos and hit that notification bell so you never miss a new video. We'll see you in the next one.